You have started transcription. Okay, thank you.
Yes.
So shall we start, uh, Madhukar?
Yes, sir. Yes, sir.
So good morning, everyone. And today we will try to cover most of the aspects of 5G radio, 5G new radio. So let's start. So as we had gone through that 5G has NG-RAN core, and then we have a data network. So what is NG-RAN? What is next generation RAN? So when ITU approved 3GPP submission, so there were two submissions by 3GPP. One was the new radio. So let me take ink here. Madhukar, if you can mute all the participants. Okay. So when it was approved, it was like uh, it was called G Node B. Just a moment. Yeah. So new radio, that is also called G Node B, is one of the NG RAN or the RAN. And other thing which 3GPP submitted was enhanced version of E Node B. So in 4G, the radio is called E Node B. So NG E Node B is also part of the 5G network as approved by 3GPP. So enhanced version of E Node B and also the G Node B. So this together forms NG RAN, next generation radio access network. Okay, so with this background, let's talk about different frequency bands which are supported by 5G. Can you guess uh, which all frequency bands are supported in 5G? Okay, so 5G, so primarily we have three ranges of the band. We call it low band, frequency band which are less than 1 gigahertz. We call it low band. So as we know that in low band, we are having 2G, that is on 900 megahertz band, GSM operates, and earlier at 850 megahertz, we had CDMA. In addition, when 3G came, the 3G also supports working in the low band, and 4G also support working in the low band. And now 5G also supports working on the low band. So as we had discussed that in respect of 5G, it can operate on all the existing bands, that is 900 band, 850 band. In addition, it can also operate on 700 megahertz band and other smaller bands. So 5G supports lower side of the band. And as we had discussed, this particular band is to support IoT services, sensor network, and the covering the remote areas or the remote villages, so that we are able to cover deep inside forest, deep inside hilly area, and in the basement with 5G. The other band is the lower side of the mid band. So when we say lower side of the mid band, basically we are talking about frequencies more than 1 gigahertz and up to 2.6 gigahertz. So in this band also 3G operates. All of you may be knowing that some of the bands within the low mid band 3G supports, and 4G of course operates on 2100 megahertz, 2300 megahertz, 2500 megahertz band. So 4G supports, and the good part is 5G also supports these bands. So straight away these band cannot be used because either 3G or 4G would already be using it. So once we close the 4G network or 3G network or refarm those frequency, then only I can use it for 5G. But 5G supports all these existing bands also. Now comes the mid band, the major part of the mid band, which is from 3.5 gigahertz and goes up to 7.125 gigahertz. So as we know that In some country earlier, 4G was operating on these bands, but very rare or minimum number of 4G network. But 5G, this has become a kind of a gold band for 5G, because most of the deployment what we see is in a band called N78, which is from 3.3 to 3.8 gigahertz, so part of the mid band. So most of the deployment of 5G initially has happened onto this particular mid band. So 4G has very less footprint, and this spectrum was free across all the country of the world. So everyone tried. So ecosystem has actually developed in this N78 band. Now we talk about millimeter wave, and we call it high band. So this is as of today from 24 gigahertz to 52 gigahertz. So these are called high band. And here no other mobile technology works except 5G. So only the 5G has support. They are the new band supported by say 3GPP or ITU for 5G. So that means uh, as we see that 2G only supported few bands, lower side of the band, and of course 1800 megahertz and 1900 megahertz. 3G also supported low band and mid band. 5G is the technology which supports all the bands as of today for different kind of use cases. For example, mid-band will be used for providing EMBB kind of uh, uh, use cases, and also the URLLC kind of use cases. And millimeter wave will be used for creating high speed, ultra high speed kind of a hotspot. So there are use cases for every frequency band which we will be using in 5G. Okay, so how these frequencies are identified, allocated for mobile, you may be aware of. So basically, it is the radio regulation sector of ITU. So as you know that ITU has got International Telecommunication Union has got three sectors. One is for radio regulation, other is for making a standard telecommunications, and third is for development. So it is ITU-R which actually identifies frequency bands for IMT. IMT is International Mobile Telecommunications. So, and then what happens that every country generally, so most of the countries are part of ITU, are member of ITU. So they follow whatever frequencies are identified by ITU in their country. So for example, in India, we follow ITU allocated or identified frequencies for mobile. And out of that, we try to give it to our service provider. Although countries are not have mandatory requirement to do so, being a sovereign country, but they actually allocate as per the ITU identification of frequency plans, ITU radio regulations. Uh, they follow that, right? So why it is important to use these harmonized frequency band which are identified by ITU, so that we have interoperability across the globe. If we use same frequency band across the globe, interoperability will be easier. Our devices will work all across the world, and also the equipment, infrastructure equipment will work. The second is that the ecosystem will develop very rapidly in a better way if we have same frequency band working across the globe. So our equipment, our devices will be cheaper because of economy of scale which can be arrived with this arrangement. Now 3GPP. So what is the role of 3GPP? So when 3GPP makes standard, for example, any SDO, when they make candidate technology for 5G or 6G, they uh, with every standard they will say that which band, which frequency band the technology will be following, and that would normally be out of the band identified by ITU. So whatever band ITU has identified, out of that only 3GPP will be using in their various releases of mobile. For example, if you look at 5G, so release 15, release 16, release 17. So they have identified certain frequency bands out of the ITU defined frequency band, and slowly they would be utilizing all the ITU bands into the standard as they develop or as they evolve. Okay, so can you guess what are the additional frequency band which were identified by ITU for 5G, considering 5G coming into the market? Any of you? So can you
In
guess?
5G
Okay,
FR1 band, FR2 band.
so
FR1 band is the
FR1,
sub 6 gigahertz band, and
very
FR2
right.
is the
So
millimeter wave 24 to 31, and V band. These bands comes there.
okay, so those FR1 and FR2 are coming from 3GPP out of the bands identified by ITU. So my question is now again slightly different, that which were the different frequency ranges which was identified by ITU for IMT 5G and beyond. Okay, let me tell that. So there is a conference called WRC, World Radio Conference. This conference is held every 4 years, and all countries, all 193 member countries participate. So for 5G, it was WRC 19, which has happened during 2019. And there, a lot of frequency bands were identified for IMT or 5G. So what were those bands? So they had identified primarily the millimeter waves, like in 24 gigahertz to 27 gigahertz range, then from 37 to 43, and from 45 to 47 gigahertz, then 47 to 48 gigahertz, and then 66 to 71 gigahertz. So these were the band identified for IMT or international mobile telecommunications, and these are in addition to all existing bands already identified by ITU. These are additional. So if you look at earlier,
what was the purpose of identifying these additional bands, sir, when it's other bands are already identified? And whether any other country is using these additional bands?
Yes, so good question. So basically, the purpose of ITU to identify frequency band is for harmonizing the use of frequencies for mobile across the globe, so that suppose whatever frequency band is operated in India, and if my customer goes to any other country with a mobile phone which is working in India, should also work in other countries. And that is only possible when, I mean, all the countries are using some sort of same frequency band. So devices would also be manufactured with those bands. So that is the major idea, to have kind of a harmonized use of frequency. Secondly, to regulate, so that interference and other things, like if satellite fellows start using the same spectrum which mobile fellows are using, so that will become a problem. So that's the idea of ITU, to identify and agree to a program. And then, so as you know that as we progress, we know how to use this higher side of the frequency band for mobile, and also slowly different frequency band gets added for mobile by ITU. So every 4 years they discuss, they do certain research, and finally they agree on to using this. So what they had seen, that 5G would require to meet ITU requirement or ITU vision of 5G, they will require certain higher band frequencies, and so that they are able to achieve 20 Gbps peak data rate and so on, and other use cases related to that. So they identified this frequency band for 5G. I hope I tried clearing your doubt.
Excuse me, sir.
Yeah.
Sir, out of these all additional bands, any band is free of cost, like ISM band for the research purposes?
So decision to make a particular band free band or we have 2.4 gigahertz or ISM band you talked about is on to a specific country, right? So it's not ITU which decides which band should be free of cost. It is specific country, a specific regulator in a country who decides. So although there is a talk going on about some of the spectrum bands to make it free, but in our country, other than those Wi-Fi bands in 2.4 and 5 gigahertz and some ISM band you talked about, so no other bands are free. Even there is a talk to make some of the bands in 6 gigahertz free, unlicensed. So, but those decisions are not yet taken. Those are not made free as of now. Did I answer your
Thank you,
question?
sir.
Thank you.
Yes, sir. Thank you.
Okay. Okay. So prior to WRC 19, so only 1.9 gigahertz of total spectrum, if you add all the bandwidth of different bands in 900, 1800, 2100, 2600, which was already allocated by ITU for mobile, it comes to be 1.9 gigahertz only. But with the above allocation by ITU, it has become 17.25 gigahertz. Almost how many times? 8 times, almost more than 8 times more allocation of spectrum for IMT or for 5G. We can see that by ITU. But these all bands like 3GPP will take very, very long time to utilize all the bands, right? In their standards. Let's look at the 3GPP standards now, that what all bands they are supporting as of now. So here comes those FR1 and FR2. One of you were trying to answer. So basically, if you look at this picture, so 3GPP has defined two frequency range, the FR1, and FR1 is starting from 410 megahertz and going up to 7.125 megahertz. If you look at release 15, okay, let me ask one question from some of you. Many of you say sub 6 gigahertz band, sub 6 gigahertz band. Why we call it sub 6 gigahertz band, whereas we are going up to 7.125 gigahertz? Any one of you?
Below 6 gigahertz means sub 6 gigahertz.
Correct, but we are going up to 7.125 gigahertz in FR1 range. So this is because let
we
me
are
answer.
covering Wi-Fi frequency, sir.
So let me try and answer. In release 15, release 15 was the first release of 5G. Sorry. In release 15, actually this frequency was going up to only 6 gigahertz. So from 400, I think it was 25 earlier, and it was going up to 6 gigahertz only. And that's why we called it sub 6 gigahertz. But in release 16, we extended it to 7.125 gigahertz. So now we should call sub 7 gigahertz band. FR1 is now sub 7 gigahertz band. So that's the difference. The other frequency range is called FR2. And this is going from 24.25 gigahertz to 52.6 gigahertz. So we are not utilizing all the in between. Suppose there is a big spectrum available from 410 to 7.125 and from FR2 these bands. So basically there are certain specified band within this range which we are using. Let me erase the ink first. Okay. So now before we proceed further and see all the bands, so many of the bands were already existing for 4G. Those are also utilized for 5G. In addition, there were 3 new bands identified in FR1 range. And these additional bands were, we call it N78, which goes from 3.3 to 3.8. And then we have N79, which is from 4.4 to 5 gigahertz. And then we have N77, which overlaps with N78 from 3.3, but goes up to 4.2 gigahertz. So some of the country follows N78, some of the country may follow N77 based on how much band they have in their country. And if you see worldwide deployment, this is the band where most of the deployment has happened. Onto the frequency range 2, up till now, I think 4 bands are defined. These are the bands: N258, 257, 261, and 260. So this is in 2.4 to 2.7 gigahertz range. This is from 26 to 29 gigahertz. And this is 27 to 28 gigahertz. And then in 37 to 40 gigahertz range. So this is our millimeter wave range. In India, we have allocated frequency in 258 band here and N78 band from here. So these two auctions had happened from FR1 and FR2. In FR1 also 700 megahertz band were actually allocated, auctioned and allocated. So any question here or shall I proceed?
Sir, I
Yes,
have
sir.
a question. Like if it is FR1 or FR2, there is a big chunk of the bands. But why we are using some specific 4 bands only if you talk about FR2 and 3 bands only in the slice of those bands in FR1? This why it is so?
So basically, when you these bands are also like identified, so that you cannot use any band. So those are identified in the standard that okay, X band or Y band or Z band will start from here and end with there. In between, whatever gap you see, there would be certain gaps, no? So there is a possibility that those bands are being used by maybe by satellite, maybe by amateur radio, maybe by some other technology. So those are already allocated for other use. That's why we are not using it on a continuous basis. And slowly we are trying to add those frequency band for mobile through WRC meetings, through other arrangements within the country. For example, earlier this N78 band in our country was not free. So we worked with defense, we worked with satellite guys, we worked with many other stakeholders, and we tried to get it free for mobile by allocating them some other band to them. And that's why we had a N78 band free for mobile communication. So there are different scenarios in different country. Okay, and that's why these are the bands. Okay, so now let's look at complete list of the bands. These were the new bands, but this doesn't mean that existing bands cannot be used for 5G. So for 5G, existing bands can also be used. So 3GPP had released those bands in their standard, and those are like this. Is this
Excuse me, sir.
visible? Pardon? Is this visible to all of you?
Yes, sir. But I am having one question. Can I ask?
Yeah, please go ahead.
Sir, that on the previous slide, what the frequencies and the N naming you had showed, is it just a frequency slicing?
So no, these are bands basically. We call it band. For example, LT bands are starting with B, B1, B2. That's a nomenclature. And the 5G bands are starting with N. N is for new radio. So you see this complete list of the bands which is supported by 5G up to release 16. So this table is taken from a release 16 document up to release 16. If you go to release 17, there will be some additional band being supported. So these all
And
bands.
sir,
Yeah.
is it these NR operating bands are specifically for any type of operations as like 900 megahertz we are specifying for GSM band and so on?
Yeah, so 900 was a GSM band initially, if you look at, but those bands are also 5G band. If you look here, so like 850 was earlier for CDMA, so we have N5 in this also. So those bands are also now part of NR band. So they are being reused for 5G. So operators, if they are able to vacate those frequency band from 2G, 3G, they can use it for 5G. Okay. Only the nomenclature is changing. Am I clear?
Sir, thank you, sir. Yes, sir. Yes,
Okay.
sir. Thank you, sir.
So just look at the NR operating band, which are name given as N1, N2, N3, N5, N7, N8, and so on. So these are the name given, right? And then you have frequency ranges given. So N1 stands for frequency starting from say 1920 going up to 1980 in uplink direction, and then you have certain frequency in the downlink direction. And the duplex mode supported in 5G is FDD, frequency division duplexing. So just see these bands. These are the FDD bands. These are all FDD bands, and these are all existing bands, right? So when we say FDD band, I have frequency for uplink and frequency for downlink separately. And our interest, major interest is in N28 band, which is 700 megahertz band, which was auctioned and Geo has actually taken. And these other bands can only be utilized once you refarm the current usage of these frequencies. For example, if you look at Airtel, they have 900 megahertz and they also have 1800 megahertz band for GSM. So they can use it like for 5G once they are able to switch off their 2G BTS and reuse the frequency for 5G. Or they should reduce usage in 2G and some of the band they can use it for 5G for supporting IoT services. So these are FDD band. So decision of FDD and TDD is also taken at standards, like ITU itself decide that a particular band can be used as TDD or FDD. Now beyond this N28, just look at these. These are all TDD band. These are all TDD band and it goes up to N51. Just see. N34 to N51. These bands are TDD band. So same frequency is used in uplink and both in downlink. Then again, we have few FDD bands here. These all are traditional bands. So what I'm trying to say that all the bands which were traditionally used in a legacy were actually FDD band because uh, although we knew TDD technology, but it was not, we were not able to implement. So only later when we were able to implement TDD in base stations and the devices, we started using that. And then we have certain bands called SDL. Can you guess what is SDL? Like, yeah, correct. So N74 and sorry, N75 and N76 are, I think these two bands are SDL. This is S is supplementary downlink. So only in the downlink direction, this spectrum can be used. So again, those N77, N78, N79, the new bands we talked about, these were the new bands identified, right? They all are TDD. All the new bands are in TDD. And then we have identified SUL. What is SUL? From N80 to
Upper
N.
link.
Yes. So this is
Uplink.
called supplementary uplink. So only in the uplink direction, these can be used and they are very, very useful. And as you see from the band, for uplink, they have actually chosen lower side of the frequency band. Lower side of the band as uplink, supplementary uplink. And there is a reason behind. Can you guess what could be reason?
Yes, the mobile
Large coverage
battery
area.
shall not be
From the
drained
mobile
more
to
quickly.
base station, it will
Mobile
be easier.
battery shall not be drained more quickly compared to base station. Base station battery should base
Coverage will be
station
more, sir,
because
lower
user
band.
should get the benefit.
Okay, other person was answering about the coverage. Can you elaborate?
Sir, like I'm Vinod Sharma, sir. What I'm
Yeah.
saying is like uplink, if a mobile handset is supposed to radiate a signal to base station, then that because of the lower side of the band, that coverage will be more. So if the handset is the mode means the distance from the base station, then also uplink, it will be possible to uplink.
Very right.
Whatever
So
details
you
you
are
got, that will be.
it's a very brilliant answer by yourself. So this is for the purpose of, like, if you have a UE or handset, okay, operating on say N78 band. So N78 band coverage would be like this in uplink direction, but downlink direction you will have a more coverage from the BTS. But in this area you cannot use the UE because uplink direction UE is not able to communicate. If I use two frequencies, one is the midband and other maybe this some of this SUL. So in uplink direction also I'll have a connection on these supplementary channels so that my mobile coverage would actually increase. So when you want to increase the overall coverage of a 5G system, you may need to use supplementary uplink channel. And supplementary downlink channel is to increase the capacity in the downlink direction. So depending upon what is the use case, you can use either SDL or SUL. Okay, now the four new bands in millimeter wave were like this here. These were the new bands. So what we see that these were the only new bands and rest of the bands were already there by ITU and 3GPP. Those can be refarmed and used, and new bands are straightforward. Countries can allocate to their operators. Okay, to summarize, just a moment. Yeah, just to summarize that we have FDD band. So these are basically LT refarming bands, LT or 3G, 2G bands, which can be refarmed. Then we have a new band, which are in the FR1 range, that is N77, N78, and so on. And then in FR2, the new bands are 257 and so on. So there are many bands. So basically, some of the bands are already identified, and these bands are like reserved. In future, these bands would be identified for any of the candidate technology being developed by 3GPP. Okay, I hope this was clear. So now we will talk about channel bandwidth. So what is the channel bandwidth supported in 5G? Can you guess? What is the channel bandwidth supported? So as we had discussed that we have frequency range 1 and then frequency range 2. So can some of you tell me that in frequency range 1, what are different channel bandwidth I can use?
Around 4.5 to
Around
5.
400
So
megahertz.
5 megahertz.
4.5
Okay.
to 5.
Okay, let me then tell you that what are different channel bandwidth which I can use. Let me erase the ink first. Okay. So in FR1, frequency range 1, we talked about, which is from 410 megahertz goes up to 7.125 gigahertz. Here, I can support 5 megahertz, 10 megahertz, 15 megahertz, 20 megahertz, and so on, and can go up to 100 megahertz. That means minimum supported channel bandwidth is 5 and maximum supported channel bandwidth is 100 megahertz. That is in FR1. In FR2, which is from 24 gigahertz to 52 gigahertz. So here I support channel bandwidth of 50 megahertz, 100 megahertz, 200 megahertz, and 400 megahertz. So the minimum channel bandwidth here is 50 and maximum is 400 megahertz. So if somebody asks you that maximum channel bandwidth supported without telling FR1 and FR2, my answer should be 400 megahertz. If somebody asks me FR1, then maximum 100, FR2 maximum 400, and there is also minimum defined. So can you tell me that why minimum 5 megahertz is required in 5G? Why do you need minimum 5 megahertz in 5G? Why I can't have 1.4 megahertz like LT. LT I can use 1.4 megahertz channel bandwidth, minimum one. But in 5G minimum is 5 megahertz. Any guess?
The channel spacing required would be more.
Pardon?
The sub-channel spacing, sub-carrier spacing.
But
I mean, if the
why is the limit of 5 megahertz? Why is the limit of 5 megahertz?
Sir, it
So
provides
that
baseline
limit,
for 5G deployment.
correct. That's there. So
I think to attain a minimum data rate, we need at least 5 megahertz.
yeah, so basically, why it is required? Because the synchronization signal in 5G, which is called primary synchronization or secondary synchronization signal, or you can call it SS block together, SSB. So this itself occupies a bandwidth of, I think in one case you need 20 RB, that means 240 number of sub carriers, and every sub carrier is 15 kilohertz. So the minimum required bandwidth is coming from the requirement of SS block. So SS block size in terms of frequency is such that you need to use 5 megahertz minimum. That's the answer. We'll talk about these SSBs later today. Okay. So now let's talk about, and we all know the access technology used in various 2G, 3G, and 4G. For example, in 2G we were using of course FDMA, and then TDMA on top of that. 3G was CDMA. 4G is again OFDMA, and 5G is also OFDMA with slight variation. All of us know. So I'll just quickly run through. Okay, now let's look at waveform and yeah. Any question? Okay, so now let's look at 5G waveform, what waveform is used and what modulation is used. So as we discussed that in 5G also we are using orthogonal frequency division, multiplexing and multiple access techniques. So you may be knowing that in case of orthogonal frequency division multiplexing, we divide the available channel bandwidth. Say, suppose I have 5 megahertz channel bandwidth. So theoretically, I divide into sub carriers. And if sub carrier spacing is say 15 kilohertz, so there'll be so many numbers of sub carriers. So here, these are sub carriers. And why we call it orthogonal? Because whenever there is a peak of one sub carrier, there'll be null of all other sub carriers. So we use OFDM waveform. And we use quam kind of a modulation. So basically we are using QPSK 16 quam, 64 quam, and 256 quam. So up to release 16, we are using up to 256 quam in 5G. Going forward in other releases, we may go beyond this 256. So this, every one of you would be knowing that when we use OFDMA, it's more spectral efficient, because in a normal frequency division multiplexing, you have a guard band where I mean closely spaced subcarriers are there, so we don't need guard band. So it's more efficient. Also, we solve many other problems. Okay, so now this is a task for all of you. That's, for example, I'll give you one example and you have to do a calculation. Suppose I have 50 megahertz channel bandwidth, and let us assume this is FR1. And then I want to use a sub carrier spacing of 15 kilohertz. And then I have a guard band. For example, if you have 50 megahertz of spectrum like this, so you have to leave guard band this side and this side. and both side this guard band is 692.5 kilohertz. So now you have to calculate the transmit bandwidth. So you have to just subtract 50 minus this number twice. So you'll get the transmission bandwidth. So can somebody calculate and tell me what is the transmission bandwidth in this case? Uh, 50 megahertz minus, you can make this as also in megahertz, like 0.6925, twice of this. So you'll get transmission bandwidth.
47 around.
Yeah, so it is 48.617. So the transmission bandwidth is 48.617. And now you have to calculate number of possible subcarriers. So you have to divide this by 15 kilohertz. Please make both side in kilohertz. So this will be 48617 divided by 15. So how many subcarrier we get? How many subcarrier we get?
3241.
Very nice. So basically number of subcarrier will be 3241. So if I use 50 megahertz channel bandwidth and subcarrier spacing of 15 kilohertz, and if I use OFDMS, I'll have 3241 number of subcarriers as the resource available to me. This is just to give an idea. And modulation, we know that we are using quam modulation in 5G. So all of you would be aware about, I should not repeat, amplitude modulation, where we vary amplitude, frequency modulation, we vary frequency to represent 1 or 0. In phase, we vary phase. And in the quam, we vary amplitude and phase together. So amplitude is also varying and phase is also varying. So, and that's why we do the quam modulation. And most of you would already be knowing that the QPSK, I'm able to transmit 2 bit per symbol, in the sense that I have 4 specific point of representation where I have certain amplitude and certain phase, and every point can represent a 2 bit. So that's why we call it 4 quam, because I have 4 points, and then 2 to the power 2 is equal to 4. So 2 bit per symbol can be transmitted. And then I have say 16 quam. So in that case, I can transmit 4 bit per symbol. So I have 16 different points having different amplitude and phase combination. Similarly, 32 quam, 64 quam, and 128 quam, and then 256 quam later on. So basically, so there is one question that generally when we practically use system, so we don't use 32 quam, we use 64 quam instead. Similarly, I don't use 8 quam, I use 16 quam. So I use only 16, 64. I don't use 128, I use 256 quam. So can some of you tell me the reason why we are only using 4 quam, 16 quam, and 64 quam, and not using 8 quam or 32 quam or 128 quam? Any guess?
Because the corner elements, the constellation, in the constellation, corner most constellation is not there in 32 and 128 quam.
So what impact it may have?
Wastage of
Okay.
transmission bits can be reduced.
You are right. So basically, suppose you have a base station, BTS, transmitting say 32 quam. So you will be able to decode that 32 quam radiation up to certain points because of the signal to noise ratio, SNR. Suppose you are able to decode up to this distance from the BTS, and beyond that you are not able to. And if you transmit 64 quam, so that also you will be able to decode up to this point, right? So the distance is not reducing for 64 quam compared to 32 quam. So it is better to use 64 quam because your UV can decode the same modulation at the same distance of 32 quam. So why to waste? So that's why we call it efficient. 64 quam is efficient in the sense that the way it is structured. So that's the one of the reason for which we use the higher. Instead of 32, we use 64. Instead of 128, I use 256 quam in practical network. Okay. So that's, we know that how bits are like represented with every position. And most of you would already be knowing how a OFDM system works. So I may not be going deep into it. So just a broad idea that, so first what we do, we map our serial data onto these constellations. So basically, I'll be making serial data parallel in the sense that suppose I'm using 4 quam. So that means I'll take 2 bits, make it parallel. Or if I'm using 16 quam, then I'll take 4 bits, serial 4 bits, and then make it 4 bits of parallel. And then I'll put those modulation onto the those orthogonal subcarriers. And after that, I'll do operation called inverse of fast Fourier transform or IFFT to make it like we'll be summing all the n subcarrier like this, and then we will up the frequency to the carrier frequency and transmit over the air. Onto the receiver side, I'm doing the reverse of it. I'm doing FFT and then quam, and finally the recover the map quam source. So it's a very kind of simplistic way of explaining OFDM system, and there are a lot of material books on OFDM. In case some of you want, you can go through that. Okay, so we have understood these aspects. So now we will talk about the concept of numerology in 5G. Then what are different subcarrier spacing? What is the concept of resource block? So starting with numerology in 5G. Okay, so what is numerology in 5G? Any one of you? Any idea about the concept of numerologies in 5G? Any idea about different numerology which we use in 5G?
Sir, is it something like a terminology like 5GC?
Okay, so it's not terminology. Basically, this is
Radio interface.
okay. So basically, in 5G, we are using variable subcarrier spacing. Variable subcarrier spacing in OFDMA. In LTE or 4G, my subcarrier spacing was fixed to 15 kilohertz. My subcarrier spacing was fixed to 15 kilohertz. In 5G, the subcarrier spacing is variable in the sense that it can be 15 kilohertz, it can be 30 kilohertz, it can be 60 kilohertz, it can be 120 kilohertz, and it can also be 240 kilohertz, right? And that's where this numerology concepts come. So basically, subcarrier spacing is like this formula, 2 to the power mu into 15 kilohertz. And here mu is called numerology. Here mu is called numerology. So suppose mu is 0. Mu is 0, that is numerology 0. In that case, what will be the subcarrier spacing? If 2 to the power 0, 15 kilohertz. Yeah, so when we say numerology 0, we mean that subcarrier spacing is 15 kilohertz. And suppose if numerology is 1 or mu is 1, then what will be the subcarrier spacing?
30 kilohertz.
30 kilohertz.
30 kilohertz, very right. And suppose now mu is 2, then how much?
60 kilohertz.
60 kilohertz, and then mu is 3, then becomes
120.
120 kilohertz,
120 kilohertz.
and then mu 4 is
240.
240 kilohertz. So we don't go beyond this. So there are 5 numerologies. There are total 5 numerologies in 5G: mu 0, mu 1, mu 2, mu 3, and mu 4. So this is the concept of numerology. So numerology 0 means 15 kilohertz subcarrier spacing, 1 means 30 kilohertz, 2 means 60, 3 means 120, and 4 means 240 kilohertz subcarrier spacing.
Sir,
So this is the concept.
Hello. Sir,
Yeah, go
why
ahead.
mu more than 4 can't be supported, as channel bandwidth maximum supported is around 400 megahertz recently you have said, right? So why not more than mu is
Okay.
equal to
Okay.
4?
So technically, yes, possible to go beyond 240 kilohertz, which perhaps will come in subsequent releases of 3GPP. 3GPP has decided to use these 5 numerologies, and this 5 numerology is good enough today to meet all the use cases, because these numerologies are also related to spectrum, also related to use cases, also related to certain aspects, like in case you want to achieve certain latency, then which of the numerology to be used and all. So as of now, 3GPP has defined up to 240 kilohertz. But yes, you are right. Technically, I can go beyond, and those will definitely come in subsequent releases of 3GPP. Did I answer your question?
Yes, sir. Thank you.
Okay. Okay, so let me go to the next slide. We have already explained this concept of numerology. Now resource block. So what is resource block? Are you aware about resource block concept in 4G?
Bandwidth time allocated to a particular resource.
Okay, so you're right. So resource block is like 12 subcarriers. In 5G, 12 consecutive subcarriers is called resource block in 5G. 4G definition of RB is slightly different, which you can read, but in 5G it is just 12 consecutive subcarriers is called RB or resource block. Okay, so that means the RB size will also be variable. Yes or no?
Yes, yes.
Because our subcarrier is variable, so RB will also be variable. So what are numerologies? Numerologies, we talked about 0, 1, 2, 3, 4. And for each numerology, I have certain subcarrier spacing here: 15, 30, 60, 120, and 240. So what will be the bandwidth of RB in case I'm using this numerology? So that is 15 kilohertz is the subcarrier spacing. I need 12 such subcarriers. So what is the bandwidth of a RB for numerology 0?
15 into 12.
12. Yeah. How much?
180. 180.
180. So basically, if you use numerology 0, your RB bandwidth is 180 kilohertz. One resource block is of 180 kilohertz. If my numerology is 1, then my bandwidth will be 30 into 12. How much?
360.
So in frequency domain, now I have 360 kilohertz as the RB bandwidth. And if you again calculate for 60, it will double, and again double, right? So basically 720 kilohertz, then 1440 kilohertz, and then 2880 kilohertz. So what is happening is that in frequency domain, my RB bandwidth is doubling if I move from numerology 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4. It is just doubling in frequency domain. So that's the concept of resource block and its bandwidth. Okay. Now again, let's do a calculation so that things become clear to me. So here I'm giving an example of channel bandwidth of 100 megahertz. And numerology, let's use 2, that is 60 kilohertz subcarrier spacing. And guard band is defined for this particular numerology as 1370 kilohertz. So you have to calculate transmission bandwidth. So how do you calculate? You have to, suppose I have 100 megahertz, then I have to subtract this guard band from both sides. Twice of this 1370 kilohertz means 1.370 megahertz. So how much transmission bandwidth I'll have? Please calculate.
97.26.
97.26.
Very nice. 97.26. And now I have to calculate number of subcarrier. And here I'm using 60 kilohertz subcarrier. So 97.26 divided by 60. How many number of subcarrier you'll get? How many number of subcarriers you'll get?
Sir, 1 point, that means 2.
No, I mean, please make it kilohertz, both unit, right? 19.26 is
1621.
2 into
1621.
yeah, 1621.
Okay, 1621. And now you calculate number of RB, resource block. Resource block is 12 consecutive subcarrier. So you have to divide it by 12. So how much RBs?
135, sir.
135.
Yes.
135.
Very right. So it is 135 number of resource blocks. So if I have 100 megahertz channel bandwidth, and if I use 60 kilohertz, I'll have 135 RB. And 1 RB is the minimum unit which is allocated to an user, right? I cannot allocate less than an RB resource for say data traffic. Okay. So suppose I use 100 megahertz channel bandwidth and 60 kilohertz subcarrier spacing. Simultaneously, how many users I can actually serve? Theoretically?
Multiply by 12.
No. So 1 RB, minimum 1 RB can be given to 1 UE, and I have 135 UE. So at a particular moment, a particular instance, I can allocate resources to how many UEs then?
135.
135. And generally you'll be allocating more resources. One RB may not be good enough. So generally you'll be allocating more and more. So I was just asking a theoretical question. The theoretically I can serve 135 users, giving them 1 RB each. If I have 100 megahertz channel bandwidth and use 60 kilohertz subcarrier spacing. If I use 30 kilohertz, then this will become double. Almost my RBs will be double. Okay. So this we have already discussed. So these are some more calculation you can do later on if you want. These we discussed. Okay, now concept of UV channel bandwidth. The concept of UV channel bandwidth. Any question?
Yes, sir. As you have said that a resource block can consist of 12 consecutive subcarriers. So my question is that why there is 12, means what that 12 indicates.
So basically somewhere
12 subcarriers to a particular user.
Correct. So basically that's a very brilliant question which you have. Why 12? So somewhere you have to like decide that how many number of subcarriers I define as an RB or resource block, so that my building block across all further things are based on RB. So basically it is in the standard everyone decided to have 12 subcarrier as an RB, and plus this was the same concept of 12 subcarrier and LT, because I have to interwork with LT and also have to do dynamic spectrum sharing with LT. So it's better idea to have the same kind of number of subcarrier as an RB, which is also there in LT. So it's interoperating with LT and also, but question is that why in LT we decided 12? So everyone agreed to use that as a building block, right? That's the answer, but you can further investigate and tell me if you have some other answer. Shall I proceed?
Yes, sir.
Okay, good.
Sir, can I ask
Yeah.
one question?
Jarur, yeah.
Changing the number of subcarriers may affect the values of our latency and the SNR values.
So very right. So basically, your question is that what is the relation between subcarrier spacing and the latency, right? Is that the
Yes, sir.
question?
Yes, sir. Yes, sir.
So yes. So basically, there is a correlation which I'll talk about between frequency band and which numerology you can use, right? So for example, higher numerologies will be used in higher frequencies. For example, if I take millimeter wave, there I will be say using 120 kilohertz subcarrier spacing. And in millimeter wave, my coverage will be small, right? My coverage will be smaller. So if you have a coverage smaller, travel time or latency of a transmitted signal to reach to destination will also be less. So I'll have a latency. And within that small period, since I have 120 kilohertz subcarrier spacing, I'll be able to pack more data onto that compared to 15 kilohertz, more data in lesser time. So I'll be able to provide you better speed at lower latency. I'll be covering that in subsequent slides if you can wait for that.
Okay, sir. Thank you.
Okay. So let's understand channel bandwidth. So as you know that for user equipment may support certain bands and certain channel bandwidth. So this is kind of a hardware. So channel bandwidth is defined here. So this the complete band supported by your device is called a channel bandwidth. But you will have to provide certain guard band as we calculated that certain guard band has to be reduced from the both side. So once you reduce this guard band, whatever is left out is called transmission bandwidth. Transmission bandwidth, and you can convert that transmission bandwidth into number of subcarrier and number of RB, which we did. And then out of all the RBs, so these are a sort of RBs. Out of all these RB on a particular time, you may not be using all the RBs. So you may be using certain number of RBs, right? Based on what allocation happens. So this is transmission bandwidth RB, and this is transmission bandwidth configuration, maximum number of RB possible in that channel bandwidth. And this is the RB which is in use or active resource block per se. So this picture I have taken from again 3GPP standard, this one. All of you can actually download this particular document from 3GPP website. If you Google it, you will be able to download and you can read these documents. These guard bands are generally, it can be asymmetric also, that you have some other guard band here and some other guard band here. So either it will be symmetric or it can also be asymmetric. I'll just explain how. But before I go, there are certain concept of the channel bandwidth I want to tell you here, that the UE channel bandwidth, right? So that this is the concept of user equipment channel bandwidth. Okay, so this is one RF carrier we talked about, but the base station can support different UE channel bandwidth, right? So single base station may be transmitting the signal on different channel bandwidth within the same BS spectrum, right? So that's the concept, please understand. And then BS also supports transmitting multiple carrier to the same UE. So if the UE is capable of doing carrier aggregation, so that's a possibility, or multiple carrier to different UE within the same base station channel bandwidth. Okay, and then UV can be configured with one bandwidth part or more than one bandwidth part or one carrier or more than one carrier. So this is per BWP. This concept is either per BWP or per carrier, per different band or carrier. So that's the concept. Okay, so I was talking about asymmetrical guard bands and symmetrical guard band. So as you know that what we discussed channel bandwidth, and from channel bandwidth I am reducing the guard band, and whatever is left is called transmission bandwidth. And you know that a subcarrier or a RB, there is some specific start point. It is not necessary that my RB or subcarrier will start from this absolute frequency. It may start slightly here. I mean, there may be, so you have to leave this much, right? So not entire channel bandwidth can be used depending upon all the PRB which is falling within the UV channel bandwidth may not be get covered. Like you have to, whatever falls in guard band and certain more, you have to leave it. Okay. What is asymmetric channel bandwidth? As I mentioned earlier that the guard band
what
is
PRB, sir? RB I've heard. What is PRB?
Physical resource block. We say PRB is same as RB. We it's a nomenclature, physical resource block. In the standard, they are using word PRB, and these two pictures are taken from this particular document TS38.101. So here, if you look at guard band is asymmetrical. Here guard band is higher. Here guard band is lesser. All because guard band depends upon the numerology I am using. So if I use two numerology within same channel bandwidth, it is possible that I use half of the channel bandwidth for numerology 1 and half of it for say numerology 2. And since every numerology has different guard band, so here I'll have different guard band and here I'll have different guard band. That's the concept of channel bandwidth and guard band. Now I want to show you this picture. This again I have taken from the same document. I would strongly recommend all of you to download and look at this particular document. What this says, what this says is like, what is the maximum transmission bandwidth a numerology can support? So this is FR1. This particular table is for FR1. And these are the numerology. Numerology 0, that is 15 kilohertz, 30 kilohertz, and 60 kilohertz. So what I am noticing here is that in FR1, I'm able to use only numerology 0, 1, and 2. That is 15 kilohertz, 30 kilohertz, and 60 kilohertz subcarrier spacing. Please mark this, that I'm able to use only 3 numerology. And how much bandwidth I can use? With 15 kilohertz subcarrier spacing, that is this one. And then these are different bandwidth, 5, 10, 15, and so on. So I'm able to go up to only 50. Just see. So with 15 kilohertz subcarrier spacing in FR1, my maximum channel bandwidth will go up to 50 megahertz only. Right? So this is going up to 50 megahertz only. Please note it down or remember. For 30 kilohertz subcarrier spacing.
Sir, please repeat it again. Sir, please repeat it again.
Okay, let me erase the ink and tell you. What I'm trying to explain that as we discussed that in 5G, we support 5 megahertz, 10 megahertz, and we can go up to 100 megahertz in FR1. But that is not universally true for all the subcarrier spacing. If I use only say 15 kilohertz subcarrier spacing, I can go up to 50 megahertz channel bandwidth here. Rest are not applicable. These are different channel bandwidth. You got my point?
Okay, sir, you are saying that what is there? 270 is written also below an RB.
270 is RB, number of RB. We calculated number of RB, no?
Okay,
so if you use 50 megahertz and 15 kilo subcarriers, RB is 270. So these are RB. Good questions. These are RBs that we calculated, and this is already calculated and given in standard. So my purpose of getting it calculated was to make you understand how these RBs and all are there. Okay.
Sir, kindly repeat why not maximum than 50 megahertz?
Okay, so there are certain regions we will look at because you may not 15 kilohertz when you use. So basically 15 kilohertz will be used in the lower frequencies, and lower frequency you cannot go beyond this 270 RB, the way bandwidths are available. So that's why, and these are defined in standard so that all the configuration in the devices in the BTS are well configured in advance. Otherwise, if you leave it, then it may not work. Okay. For 30 kilohertz, we are going up to up to 100 megahertz. Just see this. For 30, we are going up to 100 megahertz, and for 60 also we are going up to 100 megahertz channel bandwidth. And remember your 135 calculation for 100 megahertz and 60 kilohertz subcarriers. We had calculated 135 RB right here. So, so basically what we can conclude that if I use 15 kilohertz, I can go up to 50 megahertz channel bandwidth. If I have 30, then I can go up to 100. If I have 60, I have to go to 100 megahertz channel bandwidth, maximum channel bandwidth. So if I want to use 100 megahertz entire spectrum, then I'll be using 30 kilohertz subcarrier spacing. Okay. Let me take example. Now Geo is using FR1 band and 3.5 gigahertz frequency band, and they are using 100 megahertz. So they cannot theoretically use 15 kilohertz. They have to use 30 kilohertz or subcarrier spacing, that is Numerology 1. So Geo must be using Numerology 1. They can of course use Numerology 2, which they may not be using as of now, because it becomes
so
complex.
what will be the basic difference, sir, with the Numerology 1 and 2? Because if I see in FR1, Numerology 1 is even more efficient compared to Numerology 2.
Okay, so that efficiency is okay. So
meeting chal rahi hai.
Okay, so that I will answer your question when we have completed frame structures, where I'll tell you that if I use higher numerology, my latency improves. Okay. And there are certain other aspects, so that I'll be explaining you once we have gone through the frame structure concept. So please hold on this question for time being. Okay, now the guard band, if you recall, we had made a certain calculation of the guard band. So our calculation was earlier 15 kilohertz subcarrier spacing and then 50 megahertz channel bandwidth, if you recall this one. So I had used 692.5 kilohertz as guard band. So these guard bands are also predefined in the standard. These guard bands are already predefined in the standard. We did a calculation of 60 kilohertz subcarrier spacing, and I had 100 megahertz channel bandwidth, and we used 1370 kilohertz as a guard band, and we got 135 RBs, if you recall. So basically, these all are the calculation which we did earlier are actually predefined in the standard. So what is the summary? Summary is that 3GPP has specified channel bandwidth for each new radio band N1, N2, N3. Band wise also they have defined this. Okay, that what channel bandwidth can be used, what numerology can be used. Those are all predefined in the standards. Okay. Now moving to FR2, same concept for FR2. FR2, as we know that supports a channel bandwidth of 50, 100, 200 and goes up to 400. But if you use 60 kilohertz subcarrier spacing, you can go up to 200 megahertz only. Just see, 200 megahertz. These are RBs, okay? And if you use 120 kilohertz subcarrier spacing, you can go up to 400 megahertz. So if an operator want to have a 4 megahertz channel bandwidth, larger channel bandwidth, then he has to use 120 kilohertz subcarrier spacing, that is Numerology 3, and use it, okay? And the guard bands are also defined. And please remember that Numerology 4 is only used for control channels, that is SS block, and not for the data, Up to release 16, the Numerology 240 can only be used by SS block or PBCH, for control signaling, and not for the data portion or the user data. Please remember this. Okay, so now you have to tell me, with our understanding, if I am using FR1 and 15 kilohertz, what is the minimum channel bandwidth I'll have, and what is the maximum channel bandwidth I can have?
Minimum is 50.
Minimum is 5 in FR1,
Sorry,
5 megahertz, and maximum is
50.
how much?
100.
50.
No. It was 50. Just see this.
50.
FR1, I'm going up to 50. Beyond this is all not applicable. So how much? 50. And for FR1 30 kilohertz, minimum is what? Just go back and see. Minimum is 5 and maximum is 100.
100.
Minimum is 5, maximum is 100 megahertz. And for 60 kilohertz, what is the minimum and what is the maximum?
Minimum is 10.
Minimum
is 10.
is minimum
10.
is 10 and maximum is
Maximum is
100, right?
100. Yes.
100. So here 10 and here it is 100. And in FR1, do we use 120 kilohertz? We don't use. We go up to only 60. And FR1, we don't use 240. FR2 use 15 kilohertz or not?
No.
We don't use. We also don't use 30 kilohertz. We use 60. 60 is like in FR1 also and FR2 also. So minimum is 50. All of us know. What is the maximum we support? 200. And if it is 120 kilohertz, then what is minimum and maximum? Just see here.
Maximum is 400.
Correct. Maximum is 400. 50, 400. And here also 50, 400. So this is what we understood, that how much channel bandwidth minimum and maximum use with different FR1 and FR2 with different numerologies. Okay.
Sir,
Yeah.
one question, sir.
Yeah.
For these things, empirical, real, any data we have available.
Yeah. Can you repeat?
Sir, any real-time applications we can see this distribution of the channels and other thing. Any documentation you can refer.
So documentation, I am referring you to this particular standard itself. These two, if you read, it gives lot many things, right? It's a very huge document. I have just taken few item of it to explain you and to give you an idea that how it works. And you can always refer back to this 3GPP standard.
Okay, so my idea is that if any real-time lab experimental we want to make it, so how we can distribute? We can make it this channel distribution.
So basically,
and we can
yeah. So basically, when you are getting a 5G lab in your institution, so you can play with all these configurations, all these frequency bands supported, and all this configuration. Another option is the MATLAB simulation. Many of you may be using the MATLAB simulation. So there also you can try all these aspects.
Thank you, sir.
Okay. So this is summary of what we discussed, that in which subcarrier spacing, how much maximum bandwidth we use. Okay. So now we have understood different frequency band. We have understood different numerologies. So in this picture, this I have taken from one of the white paper of Qualcomm. So very nicely explained that which frequency or numerology will be used where. So let's start. So basically 700 megahertz band, which is N28 in our case, Geo is using, is an FDD band, right? And Geo has got about 20 megahertz bandwidth here. So this frequency band, when practically we'll be using, these are not the rules, but the practical aspects. Your channel bandwidth can be 5, 10 or 20 megahertz generally, because this spectrum is very scarce and you may not have more spectrum. And here I'll be using subcarrier spacing of 15 kilohertz. And this will be for outdoor coverage. This is mainly for coverage of IoT, remote area, or some sort of umbrella coverage in urban area. So Geo has deployed this particular frequency along with the mid band. Okay. So numerology 0 I am using for this kind of a environment. Suppose I am using 3.5 gigahertz N78 band. So N78 band, as I explained you, that I'll be using about 100 megahertz channel bandwidth. Okay. So I had to use 30 kilohertz subcarrier spacing, that is numerology 1. And this I'll be using in a macro and small cell in the urban area to achieve my EMBB requirement. And also I can use for UR LLC kind of a requirement. And as you know that 5G also support unlicensed band. So in some countries 6 gigahertz is unlicensed band. So in unlicensed band, I'll be using numerology 2, mu is equal to 2, that is 60 kilohertz subcarrier spacing. And here in 6 gigahertz, suppose I have 160 megahertz of channel bandwidth overall. So numerology 2, and it is for indoor coverage. This I can put an indoor BTSs, maybe in the classroom, maybe in the hall. And then I have millimeter wave. Millimeter wave in our country, we allocated 26 gigahertz. Your example given is 28 gigahertz and 258. So here I'll be using the 120 kilohertz channel bandwidth because I have to use 400 megahertz. I have 400 megahertz channel bandwidth, so only 120 kilohertz subcarrier spacing or numerology 3 can be used. I'm not using numerology 4 here because that is only used for control signaling, that is synchronization signal block. So have you understood a better idea now with channel spacing, subcarrier spacing, frequency band, and their uses? Do you have some better idea with this explanation? Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
Thank you.
Yes,
Okay.
Yes, sir.
Okay. Now earlier, some of you, this picture I have taken from empirical.com. There is a good website and they have a YouTube channel. They have very good, some of the highlight of the courses explained in a very nice way. So basically, this particular graph on x-axis, I have frequency band. For example, I have low band, medium band, high band, and very high band. Okay. And then on y-axis, right side, I have latency. And left side, I have a cell size. Okay. So you will understand it better that when I am using lower frequency, and lower frequencies have property to cover a larger distance, right? And to cover larger distance, I have to use 15 kilohertz subcarrier spacing, because in 15 kilohertz subcarrier spacing, I can, we call it cyclic prefix. I have a bigger cyclic prefix, and this avoids intersymbol interference. So practically what I'll be doing, I'll be using lower side of the band with the numerology 0 and the large coverage. With this, my latency will be some sort of medium, because travel time of signal to a larger coverage will give me not a very good latency. And suppose I want uh, a latency also, then what I can do, I can have a small coverage, this one, small coverage using say 15 kilohertz, right? And then I can have a good latency. Practically that is possible. I mean, technically that is possible. But what I am losing here is a lot of resources, time resources I'm losing, because I have a bigger cyclic prefix. I'm covering very less distance. So I'm actually losing onto the resources, right? So I had to decide correctly that which subcarrier spacing I should use for which requirement and which frequency band. So practically I'll be using for coverage and 15 kilohertz subcarrier spacing for a larger coverage. Okay. Right. And technically you can use any. If you go to the medium band, like medium band. So for example, if I use a 30 kilohertz or 60 kilohertz subcarrier spacing with smaller coverage, I have a good latency. If I have a coverage slightly larger, then I have latency will be slightly poor. But I cannot be as large coverage as the 15 kilohertz can offer, because of here CP size of 30 kilohertz subcarrier spacing, when we use 30 kilohertz subcarrier spacing, is half of the CP size of 15 kilohertz, the way it is designed. So I can cover a lesser distance. So I cannot, if I have a larger distance, the problem will be of intersymbol interference. So to summarize, in case you need latency, please use higher band with low coverage. If you requirement is a cell size, go to the lower side of the band and have a larger cell size. That's the thing we can do. Any question if you have here, or shall I proceed?
Sir, you can proceed.
Okay, thank you.
Sorry, sir. Can you please once repeat these contents for the cell size versus latency? Yes, cell size versus latency.
Okay, so suppose this is my BTS, and I'm covering a larger distance. Your UE is here, right? So what? So one of the aspect of latency is that the transmitted signal has to go to this place. So larger the distance you will cover, because it is traveling at the speed of EM wave. So larger the distance, there will be increase in latency, right? The time to reach will be more. If you have less coverage, then this distance is less. So the latency will improve. That is one aspect. So what I'm trying to say that lower frequencies have a characteristic to cover larger distance. So I will have a larger coverage, but I'll compromise on the latency. I'll have a medium, because I'm covering large. And also for IoT and the rural areas, where coverage requirement is there, I don't care about latency much. But suppose I have applications like autonomous car, where latency requirement is of say low range. So maybe I can use mid band here, 30 kilohertz subcarrier spacing with a smaller coverage, and then I'll have a low coverage, right? And this latency here, I'm able to get more on two accounts. One is the travel time because of the less coverage area. Other is because there's something called TTI, transmit time interval. transmit time interval. That means resources are allocated. So for 30 kilohertz, my TTI is half compared to 15 kilohertz. So that we'll understand once I have covered the frame structure. This you'll have a better idea after that. Should I proceed?
Sir, one question can I ask?
Yeah, please.
Sir, this latency part, when we are working on this vehicles, autonomous vehicle part, experimental things, if we want to see the district, means the absorption of the signals sometimes also happens as we see in real time. What are the kind of things that will affect the latency points when we are working in the laboratory experiment? See, sir, in real time, so the trees and other thing, forest area and other areas may be and normal urban areas is a lot of difference because of the signal absorption kind of thing. Is really it happens in this case also, or it is not?
Yeah, you're right. So basically what you're talking about is the link budget, right? One has to think about the link budget analysis for different scenario. Link budget for a open field will be different. Link budget for a urban area will be different because of the high rise building, and in the rural area you may have foliage loss in the area where a lot of rains are happening, so because of that you'll have loss. So one has to actually calculate the link budget before we actually deploy uh, uh, the any network for any use case. And we have a class on link budget which will give you a better idea on how to plan, how to do RF planning in different topographical regions, different scenarios. Okay.
Sir,
Thank you, sir. Thank you, sir.
We have a low frequency range and very high frequency range.
Yeah.
And what use cases we will have for this when we are going to have a cell size when it is small?
Yeah.
What use cases will be there for the low frequency and for very high frequency?
So low frequency use cases are large coverage, that is coverage of rural area, coverage of IoT, coverage of basement, where you may have sensors installed. So low frequencies are for that. Medium frequencies are use cases related to enhanced mobile broadband and URLLC kind of application. And for high frequencies, your use cases are like EMBB, that is example I can give. Suppose you have a stadium. Right? A stadium may there will be lakhs of people seeing the match, and everyone want to click a photo or video and upload onto social media. So data requirement would be very huge. So in the stadium, I can install certain number of small cell with this millimeter wave. So I'll be able to cover the stadium in a very, very good way, and EMBB can happen. Even the video streaming would be possible. Broadcast would be possible from the stadium using these infrastructure. And practical cases, if you look at Verizon in US, they have installed this millimeter wave thing in all the stadium of the US. Is it clear? Shall I proceed?
Thank you, sir. Thank you.
Okay. Now there is a concept of carrier aggregation. This was there in 3G, 4G, and 5G. Theoretically, 5G can support different kind of carrier aggregation, be it intra-band contiguous. That means within the same band, there are two chunk of frequency. Those can be carrier aggregated. And then intra-band non-contiguous. If there are two chunk of frequencies in the same frequency band, this carrier aggregation would be possible. And then interband non-contiguous. Suppose there is a band A, band B, there is some carrier component here, some carrier component here. So these can also be used for carrier aggregation. That means in 5G, all type of carrier aggregation will be possible. Okay, I'll give you some example of carrier aggregation which was there in LTE Advanced and LTE Pro. So if you look at LTE Advanced, that is release 10, I'm just giving a background. So there, 5 carrier up to 20 megahertz could have been aggregated. That means total of 100 megahertz channel bandwidth with carrier aggregation was possible. In release 13, they supported up to 32 CC. So these all are like a standard point of view. What got implemented was just this. I mean, if few operators have just did this, not beyond, but theoretically it was possible to have 32 carrier aggregation in release 13. But practically limitation comes in the user equipment. The user equipment has to have multiple trans and receive chain equal to the number of the carrier aggregations. If I'm doing 2 carrier aggregation, then at least twice TXRX or 4, that means 4. So those are the requirement, and that's why we are not able to use very high order of carrier aggregation practically. In carrier aggregation, what happens? This is an example. Just look at this picture, and this there is an article. I have given this particular link. You can read a 3GPP article on this. So what they do is, like, suppose you have 3 bands. So band 1 is, say, blue one, the lower band, so that it is covering larger distance, and then your band 2, which is say a higher band, which is covering this is the red area. It's a lower one. So this one, the blue one, is defined as a primary serving cell. So that means all the control channel, or we call it RRC connection, and data will be handled by blue one. But the green and red one is secondary serving cell. It is only to carry user data. It is only to carry user data. For signaling, I'm using only the blue one. So this is how carrier aggregation is used in 4G and also in 5G. Okay, so as I said that theoretically 5G should support 16 carrier aggregation, up to 16 carrier aggregation in different FR1 and FR2 bands. And also there is a possibility of dual connectivity between LTE and new radio. So that is also implemented using the carrier aggregation concept. Up to release 16, if you look at release 16 documents, the carrier aggregation up to 1.2 gigahertz of a total channel bandwidth has become possible. So I'm talking about release 16, the document which I mentioned, you can read that. And these CCs can use different numerology. That means suppose you have a carrier component 1 and carrier component 2. I can use this for numerology 0. I can transmit with numerology 0. I can transmit with numerology 2. For example, if I have a low band as carrier component 1 and high band in carrier component 2, so I can use different numerology. I can use carrier aggregation with TDD, one band in TDD, other band in FDD. That is also possible. I can also do carrier aggregation maybe with one TDD band and other, say, supplementary downlink or supplementary uplink band. So all these permutation combinations are possible in 5G. Okay, so let's look at, so this is what I said. Let's look at different use cases of carrier aggregation. What are different use cases? One is the dual connectivity. Do you know what is dual connectivity? When we say dual connectivity, what we are talking about? What is dual connectivity? Okay, if
Send and receive. Simultaneous connection given base station.
there is sorry. So basically, let's take one example.
Yes.
Dual connectivity when we have 4G and 5G radio both operating. 5G device can connect to 4G and 5G network simultaneously. So let's take an example. Suppose 4G is operating on 2.1 gigahertz and 5G is operating on midband, that is 3.5. Obviously, 4G is operating on lower bands. It will have a larger coverage. So 4G coverage is going up to the larger distance. Okay, like this. And the 5G coverage is in the blue area, which is slightly less coverage. So what will happen, although 5G coverage I am saying as a blue, but in downlink direction it is going beyond because I can transmit more power. So in downlink direction it is going here. But the device is not able to use because uplink there is a problem. But since there is a concept of dual connectivity, it will be able to connect to the system through the 4G, right? 4G coverage. So uplink direction, I am using 4G for downlink and uplink at this position, and 5G I can still be using for downlink. If I'm in a good coverage area, then I can use 4G and 5G both for uplink and downlink. So basically, with use of dual connectivity, my overall coverage of 5G is increased by this area B. Area A is the common coverage of 4G and 5G. Area B with dual connectivity, my overall coverage of 5G is increasing. So this is one of the use case of carrier aggregation in dual connectivity concept. So kindly mute your mic in case you are
Sir, can
speaking
you
to someone.
repeat it? I was not able to hear.
So Madhukar, if you can mute everyone because there is some noise coming. Okay, is my voice coming now?
Yes, sir.
Okay, so this is an example of dual connectivity. That means this base station is transmitting 4G signal as well as 5G signal, and the devices are 5G devices capable of dual connectivity. So since 4G is operating on say 2.1 gigahertz example, so it will cover a larger area. That means it will cover the green one. 5G is operating on 3.5 gigahertz, slightly higher frequency. So it will cover the blue area. Coverage is blue area. So generally the devices, 5G devices will not work on this green area on 5G because uplink will be a problem. Although from the BTS side, I can pump more power. But in case of a dual connectivity, what will happen that your device will still be able to communicate using the 4G uplink, right? So all the signaling can go through the 4G BTSs. So I can use 4G for downlink and uplink and the control signaling, and 5G I can use for downlink in this area also. That means if I have dual connectivity concept, overall coverage of my network will increase by area B for 5G devices. Is it clear now?
Yes, sir. Thank you.
Okay. So many examples. Now let's see the interband carrier aggregation. There are two bands. Like suppose NR carrier 1, NR carrier 2. NR carrier 2, let us assume to be covering a slightly lower band, so covering this much area. And the higher band is covering the blue part. And now I have a carrier aggregation between them. So here the 5G BTS is transmitting two carriers, carrier component 1 and carrier component 2. And our devices are able to receive both. If my device is in this area, blue area, it is able to transmit, uplink and downlink in both the carrier frequency. But if my device is here I have coverage of only NR carrier 2. So I'm able to do uplink, downlink in carrier 2, but I can receive downlink transmission from carrier 1 also, because from BTS downlink would be possible. So I'm able to increase coverage with carrier aggregation. So I'm able to achieve extra coverage if I'm using the carrier aggregation. So benefit what is coming is in the blue area, my data rate is more compared to not having CC, carrier aggregation, CA. And in this area, I'm increasing coverage and data rate in downlink direction is also more because of the 5G. Is this clear? Shall I proceed?
Yes, sir.
Okay.
Yes, sir.
Now let's look at the supplementary channel. This is an uplink supplementary channel. So here also similar concept that generally the midband is covering this much area only from the BTS. But in downlink direction, I can cover up to here. But because there is an uplink limitation, my devices are not working in this. But if I deploy a supplementary uplink coverage, so my uplink traffic can go in this, and downlink I can use the coverage of the midband. So this way also I'm able to increase overall coverage using the supplementary uplink channel. So this is another use case of carrier aggregation between SUL and a standard TDD or FDD band.
So in case of handoff,
yeah.
In case of handoff, how we will be taking care of using 4G or using 5G?
So so here both. So basically here both are. Just a moment. Here both are 5G, so there's no question of 4G here. Only in case of a dual connectivity, that question will come. So the handover, so since it is dual connectivity, and if you have a SA network, dual connectivity, you can use 5G, or in case you have a NSA mode, non-standalone mode where 4G is the master BTS. In that case, all the handover procedure will be done by 4G. So it depends that which base station is configured as a master base station and which base station is configured as the slave one. So depending upon that, the handover procedure will be done by respective BTS. Is this okay?
Yes, sir.
Okay, the same example here. Now, as I said that it is possible to have carrier aggregation using the unlicensed band. So just see this picture. So you have, suppose this is NSA mode, non-standalone mode of deployment. So, and you have 4G core, that is EPC core. So here you have a LT as a master base station and new radio in unlicensed band as a slave, and the device can connect to both. If it is a 5G device, it can connect to LT and it can also connect to the NR in unlicensed band. So this example is explaining how carrier aggregation can work in unlicensed band. And then your device will have the better speed or double speed using this concept. In the other example is of 5G itself, the 5G core and 5G main radio is here. And maybe in unlicensed band, I can have a radio, which is the slave configuration, right? And it's this is connected to a master new radio through XN interface. So control signal will also pass through this. So this device can actually connect to both NR in unlicensed band and also NR in the main band, and carrier aggregation is possible. So carrier aggregation using unlicensed band would also be possible in both SA and NSA mode in this configuration. Okay, is this okay? Shall I proceed?
So please repeat the previous slide.
Okay. So here what I want to explain you is that if I have one normal frequency band, and other frequency band which I have is from the unlicensed band. So can I do carrier aggregation between licensed band and unlicensed band? Answer is yes. And in this scenario, if I have NSA mode of operation, non-standalone mode of operation, meaning I have 4G core, which is called EPC, 4G BTSs, which is LT, and I am deploying one BTS of 5G NR in unlicensed band. So what will happen? LT is my master BTS. NR here is my slave BTS, right? So so my device can connect to both BTSs, dual connectivity, and have better data. So this is kind of a carrier aggregation. One carrier is in main band, licensed band, and other is the unlicensed band. This is also possible in a SA mode of deployment where I have 5G core, 5G BTS, master one, and the 5G slave BTS. Okay, and then device can connect to both. Is this clear or any more doubt?
Thank you, sir.
Okay. Okay, so shall we take 5 minutes break here before we proceed? If everyone agrees?
Yes, sir.
Yes, sir.
Yes, sir.
So maybe
Yes,
it's 11:50. We'll start at 12 again. Okay, so 10 minutes break for all of you. माथुर साहब नमस्कार. आपका माइक म्यूट है सर.
Sir, your mic is mute. We are unable to hear.
Mathur Sahab, your mic is mute. अभी भी आवाज आ नहीं रही है सर.
Sir, we are unable to hear your voice, sir.
Mathur sir, there is some issue with the mic. You have mic issue, sir. आपकी आवाज आ नहीं रही है. In the meantime, if others have anything, any discussion to be carried, we can do that parallelly.
Sir, for quizzes, do we get any score or something?
I'm waiting for everyone to attempt, and after that we will be sharing the score.
Okay, sir.
I request everyone to attempt quiz 1 and quiz 2 quickly, so that we share with everyone. Madhukar, is it going well?
Yes, sir. It is recording also.
Recording is on?
Yes.
ठीक. Screen visible?
Yes, sir, it is visible.
Okay, so let's start in 1 minute. 12, I think. Okay, shall we start? Are you ready? Some of you can say yes.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, great.
Yes, sir.
Okay, thank you. So let's talk about now BWP, that is the bandwidth part. So are you aware what is the concept of bandwidth part? Any of you? आप में से कोई bandwidth part के बारे में बता सकता है?
Not much idea, sir, but we know that bandwidth can be shared, right? So that we can the communicate multimedia data in multi-channel, and we can also see that.
Okay, so what is bandwidth part in 5G? Is my voice audible?
Yes, sir.
Yes,
Okay.
sir.
Okay, good. So bandwidth part concept in just a moment. Okay. So bandwidth part in 5G, like if you look at 4G, all the user equipment are actually designed to support 20 megahertz channel bandwidth, which is maximum channel bandwidth in 4G. So all the UE will be designed for 20 megahertz. And because the control signals are spread across entire 20 megahertz in 4G, so you don't have option to utilize the lesser channel bandwidth. That means whatever channel bandwidth you support in 4G, suppose I use 20 megahertz, so the control signaling will be spread across this 20 megahertz channel. So even if you are just browsing, so your entire 20 megahertz circuitry is on. So you are wasting energy. You are not actually utilizing. 5G, as we know, that can support very high band, go up to 400 megahertz channel bandwidth. So it is not a good idea to have that. So there is a concept of bandwidth part for two reasons. One is, even if a device supports 400 megahertz, even if one user equipment supports 400 megahertz, then this 400 megahertz channel bandwidth can be divided into multiple BWP, multiple bandwidth parts. And these bandwidth parts can be of 5 megahertz or 10 megahertz or 50 megahertz. and higher, right? So different, and that can be even overlapping. And suppose I'm browsing, so I'll be using only the 5 megahertz bandwidth part out of the 400 megahertz bandwidth I support. Or maybe I'm using 50 megahertz, suppose I'm doing a YouTube. If I'm doing a very high speed, ultra high speed thing, maybe I can use 100 megahertz channel bandwidth. So this is the concept of BWP. Let's see pictorially. So if you look at this, what this picture trying to say that all UEs support full carrier bandwidth. In 5G, I support up to 400 megahertz. So a UE can support less than carrier bandwidth, not the full carrier bandwidth as was in 4G. So UE can support less also. So this is the concept of carrier bandwidth. So that means a bandwidth part or BWP is a subset. BWP is a subset of contiguous common physical resource block. Certain number of PRBs, contiguous PRBs, certain numbers into some number is can be configured as a bandwidth part. And beauty is that suppose I have BWP1, BWP2, BWP3. Each can have its own numerology. Maybe it can support numerology 0, this can support 1 and 2, or all can have same numerology. So that configuration would be possible. And the third is that maximum 4 BWP can be configured. 4 BWP can be configured in uplink and 4 again in downlink. And in case I have supplementary link, then again 4. So for each uplink bandwidth, downlink and supplementary, I can have 4 BWP. Okay. But at a time, only one BWP will be active. That's the concept. At a time, only one BWP will be active. Let's look at certain use cases. Suppose I have this much support of say 400 megahertz channel bandwidth, but I have created a device supporting only a small chunk of frequency. Okay, so that means a UV can be manufactured on a reduced UV bandwidth. Suppose you want a device of less complexity, less cost. Example is IoT sensors. I can use a smaller part, maybe 5 megahertz, because 5 megahertz is the minimum in 5G. So I can have a BWP of 5 megahertz. I can design circuitry for 5 megahertz in certain band. So this is one of the use case. Other use case is that although my device support the overall BWP, overall channel bandwidth of this much, in this channel bandwidth, I can create 2 BWP, one having the entire and one is subset of the other. So whenever I am just browsing, I can use this bandwidth part, BWP2. In other time, I can use BWP1 when I need more data. So this is energy consumption. UE can conserve energy, right? And now suppose I have two use cases to support in different numerology. So part of the band I can have BWP1 operating on say numerology 1 and other operating on numerology 2. So I can use multiple numerology using the concept of bandwidth part. Okay. Suppose I have non-contiguous spectrum, right, in the same band. So I can define those non-contiguous spectrum as BWP. So BWP1, BWP2, and maybe this portion is unused today, and in future I can support something new which is not known today. And also the forward compatibility comes because I am able to coexist within BWP, so I can use it the rest of the bandwidth which is available for any future looking technologies, something which is new and not yet defined. I can use, maybe I can use some other kind of a waveform or modulation technique and use this bandwidth path, because these are independent. I can use a different BWP having different numerology or having different technology. In this picture also, we depict same thing. Use a bandwidth part. On x-axis you have time. This is time, and then on y-axis, this axis, I have RB or bandwidth.
Your slides are not shown.
Can somebody else confirm whether my slides are visible?
Slides are visible, sir.
Visible, sir.
Okay, so maybe I can request madam to maybe reconnect and connect so that your slides come. Maybe your bandwidth is slightly
All
poor.
right, sir.
Okay.
All right, sir. Thank you.
Okay, so you have time on x-axis and you have bandwidth carrier on not bandwidth part, but the those carrier or RB. So basically, initially when you are say browsing, you are using BWP1, which is active. And when you are doing say YouTube or Netflix, then BWP becomes active for that duration. And again, it switch back to BWP1. So basically at a time, only one BWP will be active for a user equipment, and maximum I can configure 4 BWP for an user. So up till now, up to release 16, 4 BWP is defined. So this is how BWP concept work in 5G. Okay, so
Excuse
as I
me,
was
sir.
explaining, yeah, go ahead.
Sir, BWP concept is useful both for uplink and downlink, or for downlink only, sir?
Both.
Sir, as per the use cases, that may be changed.
Yeah. So basically, it is between UV and BTS, which so there are certain predefined BWPs. Among those predefined, BTS and your devices can negotiate and set a particular bandwidth part configuration for a device. Okay.
And on what basis that has to be chosen, sir? How many bandwidth parts are to be made, or for any application to be defined or device?
Based on applications, you are right. Based on applications. Based on applications. Okay. So
thank you.
Sanjay, if you can mute, there is some noise coming. Yeah. Shall I proceed? This is important slide. Okay. Left side, what you see is a LT frame structure, and right side, what you see is the new radio or the 5G frame structure, and it is being shown one of the subframe. In 5G, the control region, the control channels are spread across the entire carrier bandwidth. Suppose I use 20 megahertz, then in 20 megahertz, this is spread. Core set is set of all the control channels. Control region set, we call it. Okay. And in 5G, what happens that now you have BWP. So one BWP is this, say it is 5 megahertz, or this may be 10 megahertz, example only. So my entire control channels are contained within the BWP. If I use two BWP, both BWP will have its own control channels. So devices are not required to look at other part of the spectrum at all, which was not true in 4G. 4G devices has to look for the entire carrier channel bandwidth, where in 5G, they have to look for within BWP. So this means I can manufacture a device supporting only 5 megahertz channel bandwidth, right? So my device can be cheaper, less complex, energy efficient, particularly for IoT use cases. Whereas in 5G, all devices comes with the entire carrier having, I mean, for the entire carrier, you have to build the device. For the entire 20 megahertz, you have to manufacture the device. That's the difference. So that's the use of BWP. Now, very important, we will talk about frame structure in 5G. So how many of you are aware about frame structure of 4G? Say yes, opening your mic, or you can say no also.
No, sir.
Okay. Okay, no problem. So I'll try to explain 4G and 5G both so that we are able to correlate. Okay. So let me divide this into two parts. One is for say 4G, and other is for 5G. So when we say frame structure, we are talking about time domain. So frame size in 4G was 10 millisecond. The frame size is 10 millisecond in 4G. In 5G also, it is same 10 millisecond. Okay. And every frame will have 10 subframe. So this is divided into 10 subframe. In 4G and 5G also, you have 10 subframe. So what will be the duration of subframe? If I have 10 millisecond divided by 10, how many? What is the time of subframe? So this is 1 millisecond. 1 millisecond in 4G and 1 millisecond in 5G. And then there is a concept of slot. So one subframe in 4G have 2 slots. So what will be the duration of slot? 0.5 millisecond. So here comes the difference. In 5G, the slot duration is depending upon numerology. So numerology may be 0, 1, 2, 3, and 4. So for numerology 0, that is 15 kilohertz subcarrier spacing, the slot size is 1 millisecond. What is the slot size? 1 millisecond. For numerology 1, when I use 30 kilohertz subcarrier spacing, my slot size will be half. So how much it will be? 0.5 millisecond. And then numerology 2, it will become again half. How much? 0.25 millisecond. Numerology 3 will be half of it. How much?
0.125.
0.125. 125. Okay. And numerology 4. What is numerology 4?
0.0625. 0.0625
millisecond. Okay. So now let us understand before I go to the symbols that in 5G, I have variable slot depending upon the numerology, and these slots are also TTI, transmit time interval. Transmit time interval, meaning by that, suppose a user equipment want to use some data, transmit some data or receive some data. So it is allocated resources, RBs, for a certain period of time. That allocation happens every slot duration. For example, if I use numerology 0, so every 1 millisecond resources are allocated, right? So your user equipment may be required to wait for 1 millisecond to get resources, right? So the latency increase would be how much? By 1 millisecond is the wait time, maximum wait time. So your latency would deteriorate by at least 1 millisecond, right or wrong?
Yes, sir. Yes, sir.
Yes. If I use numerology 1, where my TTI is 0.5 millisecond, that means every half millisecond, I'll be able to allocate a resource to a user equipment if required. So my impact on latency has reduced by half, right? If I use say numerology 3, then it is 1/8 of a millisecond, right? My TTI is 0.125 millisecond or 1/8 of a millisecond. So tell me that if I go higher in numerology, my latency will improve or deteriorate?
Improve.
Yeah, improve.
Improve.
And in 5G, 4G, this was done at subframe level. That means every 1 millisecond resources are allocated. So your device has to wait for 1 millisecond to get resources. So that's how latency has been improved in 5G. That's how latency have been improved in 5G. And just recall this 1 millisecond, what is my subcarrier? 15 kilohertz, right? So in 1 millisecond, I'll be using a subcarrier of 15 kilohertz. Here I'll be using 30 kilohertz. Here I'll be using 60 kilohertz and so on. So that means I am increasing the frequency resource, doubling the frequency resource, and going half into the slot duration. So although my slot duration is becoming half, my this particular frequency is doubling. I mean the subcarrier spacing is doubling. Okay. Now what is symbol? In one slot, how many symbol can be accommodated? So are you aware about 4G?
7 symbols.
Yeah. So 7 symbol in 5 milliseconds. So in 1 millisecond, they will have how many? 14 symbol. In one subframe of 1 millisecond, in 4G, I can have 14 symbol. So now in 5G, since my slot is 1 millisecond, for this numerology 0, I have 14 symbols.
Sir,
how many symbols?
How 7 symbols in 4G?
Pardon?
How 7 symbols in 4G?
So this slot is divided into a smaller time where these symbols are transmitted, and symbols are nothing but subcarrier for that much duration, right? So as per standard, I have 7 symbols in 0.5 millisecond. So in 1 millisecond, I'll have 14 symbols, right?
Okay.
In 5G with numerology 0, that is 1 millisecond slot, I have 14 symbols. How many symbols I have? 14.
14. Yeah.
So with 0.5 millisecond, I'll have 2 slots, right? I'll have
2 slots.
in one subframe, I'll have 2 slots, right? So in 1 millisecond, how many symbols I can transmit?
28.
28. And it will go on doubling. It will go on doubling. So that means the time has reduced and number of subcarrier spacing has increased. So within 1 millisecond, my capacity to transmit data is doubling. Am I right or wrong?
Yes, sir.
In the same 1 millisecond, now I am able to transmit 28 symbol and double when I go higher in numerology. So the data speed offered would also be more if I go higher in numerology. Am I right or wrong?
Yes, sir.
Right, sir. Right, correct.
Okay. So same thing in a pictorial way, that frame size is 10 millisecond and every frame is divided into subframe of 1 millisecond. So I have 10 such 0 to 9 subframe in 10 millisecond one frame. And this 1 millisecond is divided into slots, and slots, even you have a formula, 1 millisecond divided by 2 to the power mu. If mu is 0, it is 1. If mu is 1 half, 1 4, 1/8, 1/16. So you have so many number of slots, and these slots are again having 14 symbols. 14 symbols. Every slot will be 14 symbol, and then slot sizes are different. 1 millisecond slot, half millisecond slot, 1/4 millisecond goes up to 1/16th millisecond for numerology 4. And every such slots can have 14 number of symbols. So number of symbols would increase per millisecond, double. There is one thing mentioned here that for numerology 2, for mu2, that is 60 kilohertz subcarrier spacing, number of symbols in some cases, particularly in FR1, will be 12 symbol instead of 14. Number of symbol per slot will be 12 instead of 14. Any of you know reason about having only 12 symbols using numerology 2? Any idea? Any of you?
Carrier prefix or pilot channel signals will be sent in other 2 milliseconds, sir.
So basically FR1 generally be used for covering a larger distance, but the CP size, like the cyclic prefix, which avoid inter-symbol interference due to multipath, reduces by half. Whatever we use in numerology 0, numerology 1, I have half of that. So numerology 2 again half. So in case I cover a larger distance, what will happen is that inter-symbol interference. So to avoid inter-symbol interference, I'll be using a slightly bigger cyclic prefix or numerology 2 in FR1. And since I am consuming some of the time for CP, cyclic prefix or time guard, I'm able to accommodate only 12 symbols. That's the answer. Have you understood? Should I proceed? Is it okay?
Yes, sir.
Yes, sir.
A slow voice means there's some difficulty. Okay. Let's understand again. So in a different pictorial representation, this I have taken perhaps from empirical.com. So here also it's shown that 10 millisecond frame in which I have 10 subframes 0 to 1, 0, 1 up to 9. And then one subframe of 1 millisecond, I can accommodate 14 symbols if I use 15 kilohertz subcarrier spacing. If I use 30 kilohertz, then my slot duration becomes half. So 2 slots, so I can accommodate 14 symbols here, 14 symbols here, so total 28. If I have 60 kilohertz, then again I can have 4 slots within the 1 millisecond. So I can have 14 into 4 number of symbols, and here 14 into 8 number of symbols. Okay, that's the slot length, how it is decreasing and number of slots increasing, doubling. Okay, so now if you have understood, please help me to fill up this chart. Okay, so I need your answers just to make you understand. Suppose you have 15 kilohertz subcarrier spacing. So how many slot per subframe in 1 millisecond? How many slot will be there?
14.
Slot I'm talking about, not the symbols. So you have frame, subframe, and slot.
2.
One.
One
slot.
Yeah,
Why
one slot.
one? Because 10 millisecond frame, 1 millisecond subframe, and slot duration is also 1 millisecond for numerology 0. Okay, for numerology 2, how many slots now per subframe?
2.
Yes, because it becomes 0.5 milliseconds. So in 1 millisecond, I'll have 2. And for 60, how much?
4.
3.
4, not
4.
3, double, it will double. Then 120,
8.
8, and then 240, 16. Now let's look at symbol per subframe. In 1 millisecond, how many symbols? So one slot contains 14.
14.
Right? So how many symbols? 14. So here symbols
28.
28, then
56.
then
112.
112.
right. Right?
224.
Now, how many slot per frame? So now I have a 10 millisecond frame. So in 1 millisecond, 14. So in 10 millisecond, how much?
140.
140,
140.
280,
280,
560, 1120.
1120, 2240.
2240.
Okay.
Those are slots.
Sorry. So this calculation I have done for this column
Symbols.
and everyone. Okay. Okay. And then in respect of slot per frame, how many slots? So chunki slot size is 1 millisecond, so I'll have a 10 slot,
10 slot.
20,
20,
40,
80,
80
and 160.
Great. So every one of you have understood if you are able to do this. Okay, so again, some calculations so that everyone is clear. So this is a frame of 10 millisecond, 9 subframe, 15 kilohertz numerology, that is 1 millisecond. So what is frame duration? Just tell me, I'll write. Frame duration here is? Please speak. What is the frame duration?
10 milliseconds.
And subframe is?
1 millisecond.
1 millisecond.
1 millisecond.
Slot per subframe?
1 millisecond.
Slot,
1
slot, 1 is the number. And slot duration is? 1 millisecond.
1 millisecond.
And how many symbols?
1 symbol.
14.
And symbols per subframe?
14.
14.
Symbols per slot is 14 and per subframe 14 itself because
14.
equal, and per frame is 140.
140.
Okay, so all good answers. For 30 kilohertz subcarrier spacing, when I have 2 slots in 1 millisecond, so now frame duration is of course 10 millisecond
10 millisecond.
and subframe is 1 millisecond. How many slots now?
2.
28.
Slots.
Two
1, 2.
slots.
And slot duration is?
0.5.
0.5
millisecond.
millisecond.
How many symbol per slot?
28.
14
Always 14 per slot.
14.
Per slot.
Per slot.
Per slot.
Per frame.
And per subframe is?
14.
14 plus 14, no? 14 here, 14 here. 28. And per frame? 10 frames are there. So 10 280. Okay, great. Now for 60 kilohertz, please let me know. 10 millisecond.
10 millisecond.
1 millisecond. How many slots now? How many slots now? 1, 2, 3, 4.
4.
What is the slot duration?
0.5 millisecond.
And how many symbol per slot?
14.
7 plus 7.
14. No. 14 only. So every
14.
14.
And into 4.
14,
56.
14, 14.
56.
Okay. And sometime it may be 12 also because of the 60 kilohertz subcarrier spacing. But our calculation, let's do with 14 only. So symbol per subframe
56.
56 and per frame is 560, right?
560. Yes.
Great. So for 120, let's do the quick calculation. Here, slot per subframe. How many slot? 1, 2, 3,
8.
4, 5, 6, 7, 8. 8. Slot duration has become 0.125
millisecond.
This 14 symbol per slot will remain. And then 14 into 8, how much?
128.
112.
And per frame is 1120.
0.
So similar is for 240, right? So I'm not asking you to do this. It's already here. Okay, so this is the summarized frame structure. I made this in an Excel sheet for all of you and taken a screenshot. So same thing which we discussed is tabulated here in different things. So now you know that slot duration is becoming half. If you go in numerology, number of slots in a 1 millisecond is doubling 2, 4, 8, 16. And number of symbol per 1 millisecond is doubling 14, 28, 56, 112 and 224. Okay. So one thing which I wanted to explain here is that although we are reducing in time domain, we are increasing in frequency domain. For example, 30 kilohertz frequency domain, my subcarrier size is double, and double. So that's the idea. That time domain, I'm going half. Frequency domain, I'm going double. If you visualize in this particular picture, here in 1 millisecond, I have 14 symbol. In here half millisecond, I have 14 symbol. Here in 1/4 of millisecond, I have 14 symbol or sometime 12 symbols. And here in 1.125 millisecond, I have 14 symbols. And frequency domain, we are doubling. Frequency domain, we are doubling just to visualize. Okay. Very important now. There's something called resource grid. What is resource grid? Any idea about resource grid?
No, sir.
Okay. Let me explain. So resource grid, it's similar concept in 4G is just remember 1 millisecond. So 1 millisecond is what? Our subframe size. 1 millisecond in time domain. And this is in time domain. And whatever number of subcarrier you may have depending upon your bandwidth. So X number of or N number of RBs, source block in frequency domain. If you plot, this is called resource grid. On the right side, you see, right side, this axis is your 1 millisecond time domain. So there will be certain number of symbols, right? So how many symbols will be there in 1 millisecond? In 1 millisecond, how many symbols will be there?
14.
14 only when you have mu 0, right?
Yes.
Right.
If you have mu 1, then 28 and so on. So on time axis, that's why you see say symbol 0, symbol 1, symbol 2, ... means that it can be 14, it can be 28, it can be depending upon which numerology I'm using, right? Onto the frequency domain, these are RB, say RB0, RB1, and so on. So many RBs, depending upon how much channel bandwidth I'm using. I can use 5 megahertz, 10 megahertz, go up to 400 megahertz. So number of RBs will depend upon the channel bandwidth I'm using. So this particular diagram is called resource grid. This particular diagram is called resource grid. Is it okay? Is this okay? Okay,
Yes, sir.
so just look. So resource grid is one subframe in time domain, that is 1 millisecond, and full carrier bandwidth in frequency domain, that means n number of RBs. For each direction, there is a separate resource grid. For uplink, you have a resource grid. For downlink, you have a resource grid. For each antenna port also, you may have separate resource grid for uplink and downlink. For each numerology, you will have a separate grid. So there can be multiple grid in use. Okay. So the same picture we have rotated from x-axis to y-axis to explain you again. So please look at this. So same picture just rotated. So this is 1 millisecond. This is 1 millisecond in time domain. That means one subframe. One subframe duration is always 1 millisecond. So these are symbols, and this symbol can be either 14 if I have numerology 0, or 28 or 56, or and on frequency domain I'll have RBs like resource block. So RB0, RB1 and so on. Okay. So basically it is subcarrier. In this picture, these are subcarriers. Subcarrier 1, 2, 3, 4. And this 12 subcarrier, any 12 subcarrier consecutive one, we can call it as an RB. Okay, now if I look at one box, this box is nothing but one subcarrier in frequency domain and one symbol in time domain. So this is one subcarrier in frequency domain and one symbol duration in time domain. One symbol duration in time domain. And this is called RE, resource element. This is called, each box is called RE. This blue one or any box is called RE, resource block, and this can be addressed using KL. K is subcarrier and L is symbol 0, symbol 1, symbol 2, and so on. So this is how we do it. Okay, now I'm giving one example. I had taken 5 megahertz channel bandwidth. 5 megahertz channel bandwidth. Numerology is 0. That means 15 kilohertz subcarrier spacing. So if you calculate, you will get about 300 subcarriers. You'll get about how many subcarriers you'll get? 300. And if you divide this by 12, you'll get 25 RB. So I have plotted on this graph. Here numerology 0 means I'll have 14 symbols in one slot. So I have plotted symbol 0, 1, 2 up to 13. On x-axis my frequency. So I have 300 subcarriers. So subcarrier 0, 1, 2, 3 goes up to 299. So this is some sort of resource grid will look like if I have 5 megahertz. This also I tried drawing in an Excel sheet just to explain. Other example is that if I take now 10 megahertz, 30 kilohertz. So 10 megahertz, 30 kilohertz means I will have how many symbols per slot? How many symbols I'll have per slot?
28.
28. So I have taken 0, 1, 2 up to 20. Sorry. Just a moment. Okay, this one. So 30 kilohertz. So I have 28 and I'll have 24 RB because I'm using 30 kilohertz. So if I divide this 288 subcarriers by 12, I'll have a 24 RB. So I have a total of 288 subcarriers. So now this grid will look like this. So number of REs have actually increased. You see that number of REs gets increased if you have more number of subcarriers or you have. So that way, I think there are some examples given. Okay. Now let's look at scheduling part. Should I continue? Any question so far?
No, sir.
Shall I continue? Yes or no?
Yes.
Okay.
Yes, sir.
Yes, sir.
So there is concept of slot-based and mini slot-based scheduling in 5G. That means our TTI is the slot duration. Transmit time interval in 5G is equal to slot duration. In 4G, it was subframe. In 4G, it was subframe. That means 1 millisecond was TTI in 4G. In 5G, since it is slot duration, that means it can be 1 millisecond, half millisecond, 1/4 millisecond. It can go up to 1/16th millisecond. So suppose you have a heavy downlink transmission and uplink traffic is less. I'm talking about a TDD environment, right? I'm talking about a time division duplexing environment. So what will happen? Slot duration, suppose whatever is the slot duration and whatever number of symbols are there in that slot, depending upon numerology 0, 1, the entire slot I can allocate for downlink and very small part of the slot I'll give for uplink if my requirement is of downlink. In case I have more requirement in the uplink direction, then during the slot duration of 1 millisecond or half millisecond or 1/16th millisecond, depending upon which numerology I am using, I can allocate all the resources for uplink, very small resource for downlink, right? And there is something called LBT, Can any of you tell me what is LBT? Are you aware about LBT?
No, sir.
So LBT is this technology is there in the Wi-Fi which we use. Listen before transmit. LBT is listen before transmit to avoid some sort of collision, right? In an environment where. So this technology in 5G is for, since we operate in unlicensed band also, where there may be other transmissions. So there will be a listen before transmit. So basically for that environment, there will be certain gap when we can start transmitting downlink or uplink. Then there is some concept of mini slot, which I'll talk in next slide. I'm reserving this for next slide. And then suppose you have a EMBB environment where data speed requirement in downlink is very high. Data requirement in downlink is very high. Then you can aggregate more than one slot. That means when you allocate resource per millisecond basis, you can aggregate more than one slot and allocate resources for upcoming slots also, so that the heavy downlink transmission would be possible and a small chunk for uplink maybe in the next slot. Similarly, for uplink direction, I can also aggregate slots. More than one slot I can allocate to a user equipment on a particular TTI time. So this is scheduling, normally slot based scheduling, so which goes up to 1/16th of a millisecond. Now, what is mini slot scheduling? So generally, it will not be possible to allocate a resource when a transmission is going on in that particular slot. But in 5G, there is a concept of mini slot scheduling wherein I can puncture a ongoing slot. I can puncture a ongoing slot. For example, suppose this is one slot, this is the next slot. The next slot is going on, and then there is a request coming for data from a user equipment, which is some sort of URLLC type applications being used. So it is possible to puncture a slot somewhere and allocate some of the symbols for that application, some of that for application. So this is kind of for supporting URLLC where latency requirement is very stringent. So to make more better latency supporting URLLC, I can puncture even a ongoing slot. As I know that I can have a TTI of 1/16th of a millisecond. And within 1/16th of a millisecond also I can puncture. So my latency will further improve. But in this puncturing, there is some configuration that either I give 2 symbol or I give 4 symbol or I can give 7 symbols. These are the configurations given in the standard. So this is the kind of a minimum scheduling unit in 5G NR. So it can go even beyond 1/16th of a millisecond, lower than 1/16th of a millisecond. Any doubt here, or shall I proceed? Any doubt, or should we proceed?
You can proceed, sir.
Okay, great. Okay, thank you. So mini slot I have explained. So use case is URLLC, as I spoke, and then dynamic spectrum sharing is also concept in 5G where this you need new radio or LT coexistence. So there also this can be used. Okay. This is very good picture I have taken from somewhere. I think I have given a link below. Very, very interesting picture how it can look like. So this is frequency and time domain. So basically, this is your time domain and this is your frequency domain. So basically what we are trying to say is the first one is scalable TTI. Transmit time interval is scalable because as I discussed, it can be 1 millisecond, it can be half millisecond, it can be 1/4 of a millisecond, it go up to 1/16 of a millisecond. So TTI is scalable, right? So depending upon what is the requirement of latency, what is the use case, I can definitely use a required TTI. Second is that self-contained slot structure. So within the slot itself, within the slot which gets allocated to user, that is self-contained. That means scheduling info, data, acknowledgement, everything is carried onto the same slot. So there are many symbols in a slot. So it's a self-contained. Self-contained also come in case of a BWP. Within the BWP, all control channels are there. So self-contained structure of 5G that makes, different from 4G or from other technology. And then you can use it, these symbols or slot, either for downlink or uplink in a dynamic direction. There is no pre-configured, like if you look at 4G, there are certain configured number of uplink, downlink symbols used. Here it is dynamic. You can dynamically, system can decide, right? So it's more faster switching can be done, flexible capacity allocation, these three aspects. The other thing is about forward compatibility. That means it is possible that within the carrier bandwidth, I can keep some of the resources free. I'm not using these resources so that it is forward compatible, right? I can use any other technology. So other technology which got used in release 16 is coexistence of narrowband IoT, NB IoT. So NB IoT system operate in some of the subcarriers, and it will not interfere with 5G. So it will coexist. And then it is integrated framework. When I say integrated framework, in the same framework, I can have EMBB, I can have V2X, D2D, I can have multicast. So within the framework, I can have multiple subcarriers, right? I can have multiple subcarriers for each of these applications, multiple applications. Then I can also support mission critical transmission by like puncturing the slot itself. We talked about puncturing the slot itself for URLLC. So mission critical transmission is taken care of. So this is kind of called as a flexible framework. Any question here, or shall I proceed? Please say yes, no, so that I understand that.
Please carry on.
Yes, sir.
So this may be going heavy a bit from 10 a.m. Okay. Okay, it is important to go through because tomorrow there'll be more complex subject which will be taught by Professor Abhay. So I thought I should give you all background so that whatever he speaks about, you are able to correlate. Okay, so this is now I'll be talking about what is a timing unit and cyclic prefix, and maybe I'll be a bit faster. But if you have any doubt, you can tell me. So timing unit is nothing but sampling time you are talking about. So every communication technology will have sampling rate and sampling time.
How DL and UL allocation is done, like based on application?
So you are not audible. So can you repeat? You had some question. Can you repeat? Okay, maybe later you can ask. So in 5G, the sampling time is defined in standard like this. Sampling time is 1 oblique this delta F. Delta F is a subcarrier spacing, and here we take maximum subcarrier spacing. And then this is the FFT size. We know that we use fast Fourier transform, and when we have number of bins in FFT size, so that we do it. So now I'll request all of you to calculate TC like this. So 1 oblique this max subcarrier spacing, although I talked about going up to 240 kilohertz, But in standard for calculating TC, they have taken 480 because maybe in future they can use 240 kilohertz subcarrier spacing also, and 10 to power 3 because it is in kilohertz. And maximum FFT size will be 4096 because our number of subcarriers are more than 3000 plus. So I can have a bin size of 4096 only. So can somebody calculate and tell me what is the sampling time in case of 5G? Please calculate and let me know. You can tell me in nanosecond. A quick calculation. Please help me by calculating TC.
0.509.
Very right. So it is 0.509 nanosecond. Now let's calculate timing unit of LT from the same formula, in the sense that here subcarrier spacing is always 15 kilohertz, and number of subcarrier we have around 1200, 1300, 1400. So I can use a bin size of 2048. So can you calculate now the timing unit in LT or sampling time of LT with this formula? And tell me what is the time. Okay, it will come to 32.55 nanosecond.
32.55
Nanosecond. And can you divide 32.55 4G time with 5G timing unit of 0.509? How much it will come?
60.
65, 66.
64. 64. So basically this is a constant which is 64. And so that means 5G is 64 times granular in terms of sampling time compared to 4G. Okay, so sampling rate is 64 times faster. So that means your device has to have more compute, your BTS has to have more compute because sampling rate has actually increased. And with this sampling time, you can calculate frame duration and subframe duration with this formula. So this is maximum is 480, that is 48000. NF is 4096 divided by 100 multiplied by TC, timing unit of 5G. So this will come 10 millisecond and your subframe will come 1 millisecond. So this 10 millisecond, 1 millisecond is coming from this formula. Now let's look at what is intersymbol interference. Can some of you tell me what is intersymbol interference?
When you transmit the data, there is an interference between your transmitted data while receiving it.
Yeah, right. So when you transmit data, there may be multi-path. So your symbols would be reaching in a different time. In this example, from this base station, one path is this, one path is this, one path is this. So 3 paths you're receiving the data. And then maybe there is a possibility that from one path you have already received data A, but during the same time, data A has been received here, but from the other path, you are still receiving data A or symbol A, and parallelly symbol B you are also receiving. So this is the area where there will be a intersymbol interference. Okay. So how can I avoid intersymbol interference? How can I avoid intersymbol interference?
Synchronization.
Broadband.
Equalizer. Tonality feature using.
So for this duration, I can create some guard time.
CP, by adding CP?
Correct. So CP is nothing but a guard time. Theoretically, it is a time on which we can call it as a guard time. So suppose instead of a guard time, what I am doing, I am copying the future part of the wave for that much duration and putting before the symbol. Putting before the symbol. You can understand with this picture that later part of a OFDM symbol, I can copying and putting in front of it. So that's why you call it cyclic prefix. So my question to
we are doing cyclic prefix, then null is created there.
Yeah. So my question is that can we keep CP as a just a blank instead of using copying this part of wave onto in front of the symbol? Can I just keep a time guard or the blank? Is it possible?
No,
I
sir.
think no.
Yes,
No.
we can, but problem will be that orthogonality will break. Whereas if you put this portion, it is still orthogonal. So to maintain orthogonality, we use CP instead of keeping a blank time guard. Okay, so the time guard or the CP, cyclic prefix, we are calling. We call it normal cyclic prefix in most cases. But in case of a 60 kilohertz subcarrier spacing, particularly when used in FR1, we use extended CP as I had explained, the bigger size of CP. So normal doesn't mean that all CP are same. So CP size, like CP size of this will be half of above and then half. So basically CP size is reduced. I'll explain you how. Just look at this picture, how CP size is reducing cyclic prefix. So these are symbols. So in 15 kilohertz environment, I have 14 symbols, 0, 1 up to 13. So these are cyclic prefix. These are in time domain, these are cyclic prefix. These are cyclic prefix. Okay. And that cyclic prefix at 0.5 millisecond. This is the 0.5 millisecond point. I have a slightly bigger cyclic prefix. And during start also, I have a slightly bigger cyclic prefix. Okay, now let's move to 30 kilohertz. In 30 kilohertz, I have now 28 number of symbols. So here, this one, 0, 1, 2 can go up to 27 in 1 millisecond. So here you can see these are the CPs. This CP size compared to this is half. This CP size compared to this is half. But again, the CP size at 0.5 millisecond point or start is slightly bigger than this. If you go to 60 kilohertz, I have 4 slots. So again, my CP size has become half. And at the center, 0.5 millisecond, I have slightly bigger CP. Is this okay?
Yes, sir.
Say yes or no?
Yes, sir.
Yes, sir.
Yes,
Now,
sir.
since already 1 o'clock, can you allow me about 20-25 minutes more?
Sure.
Say yes.
Yes, sir.
Yes, sir.
Yes.
Okay. So it may become slightly heavy for you, but please let me finish this because tomorrow we have a session from 10 itself related to all aspects. So I do not want you to miss that. Okay. So we will do some calculation. We are going a bit complex, but this will give you an idea. How to calculate cyclic prefix is given by a formula in the standard. So one is for extended cyclic prefix for 60 kilohertz, as you know. Other is for normal, to normal. So here we had seen that cyclic prefix at 0.5 millisecond is slightly bigger. So the formula is here that symbol 0 and symbol 7.2 to the power me, that is 0.5 millisecond point. And these are for rest of the symbols. So how do you calculate? So TCP, time for a CP, is NCP divided by timing unit we calculated in nanosecond. So if I have to calculate TCP, suppose I have to calculate TCP for 15 kilohertz. So 15 kilohertz and normal CP I have to calculate. So basically at symbol 0, ye wala formula. If I use this formula, okay, so NCP is equal to 144 into K. K we had calculated as 64 and into 2 to the power minus mu, where it is 0 in my case. So becomes 1. and then 16 into 64 plus 16. So how much number of CP I have, number of samples we can say. So I have 10,240 samples. So in terms of TCP, now I can multiply it by TC. So I can get cyclic prefix duration. So 5.2 millisecond. So what is the duration of a cyclic prefix? 5.2 microsecond. Microsecond, right? Did you get this? If you get this, then you calculate for this at symbol not at 0.5, this formula, using this formula. Can you calculate and tell me the NCP? How much NCP? 144 into this one. 144 into 64 into 1. How much it will come? Can somebody calculate for me?
9216.
9216.
9216.
Very right, 9216. And then you multiply that into TC. TC was 0.509 nanosecond. That will give you the CP size. Tell me in microsecond. 4.69. Very right. So 4.69. 4.69. So that just see that 5.2 microsecond is the normal, and at symbol 0 and symbol middle symbol I have 4 point slightly bigger. You got my point? Okay. Other calculation is for 60 kilohertz. This one 512 into 64 into 2 to the power minus 2. How much will be the NCP? Calculate. 512 into 64 into 1 by 4, because 2 to the power minus 2 is 1 by 4. So how many number of samples? 8192. And multiply this by TC, you'll get 4.17 microsecond. So basically you don't need to calculate. Standard has already given whatever we calculated, say 5.2 millisecond, it is here, 4.69 millisecond here. For 60 kilohertz we had calculated. So basically these are given in the standard itself. All these values are already available. Calculation we did for understanding. Okay, then we can also calculate symbol duration using whatever we know, that if you just add whatever you calculated this, right, and divide, so you'll get total symbol duration, subtract that and divide by 14, then you'll get the symbol duration. So symbol duration is 66.67 microsecond or numerology 0. So what is the duration of a symbol? 66.67 microsecond. Is this okay? Any doubt? Is it going heavy?
Okay, sir. Okay, sir.
Okay, yeah, right. So this is also given, like if you read the standards, there is a table given that what will be the symbol duration. So just see the symbol duration here. For 15 kilohertz, it is 66.67. And the symbol duration in this is almost becoming half, then again becoming half, then again becoming half, again becoming half. Right? So symbol duration is also half. And in this duration, I have a more frequency like 30 kilohertz, 60 kilohertz of the subcarrier. Within that duration, I'm able to push. Okay. And because of the CP, how much overhead I am creating, those calculations are given here.
Sir, you are not audible.
Am I audible to everyone or?
Sir, audible, sir.
Okay, so maybe you need to look at your connectivity bus. Maybe you can reconnect. Okay. Similarly, you can calculate multi-path distance also, because you know the EMF wave, like you know subcarrier spacing, and for that you know the CP, cyclic prefix, and you know the EMF wave. So you can calculate the distance travel. So it is 1407 meter. Simple. So that means we were talking about multipath. So a cyclic prefix decides that how much distance I can cover considering how much multipath I am having, how much multipath distance. So this is some sort of multipath. So if I am using 15 kilohertz subcarrier spacing, I can cover a maximum of 1407 kind of a distance. If distance means the entire going and coming distance. So for every calculation, you can do the distance calculation. So this is given here, that how much distance I can cover. Multipath, not the distance. What is the multipath I can tolerate? Otherwise, I need to use higher CP. Okay, the last topic today is the synchronization process, which I'll take about 20-25 minutes. I'll be trying to explain. In case you want to go this process in a very slow way, slow lecture, there are other lecture which I have put on YouTube. You can go through. Today we'll go slightly faster, but you can still ask question. So the synchronization which I'm talking about is called synchronization signal block, SS block. This was also in 4G. So this is time domain and frequency domain. So in time domain, it covers 4 symbols. There are 4 number of symbols required to carry SS block in time domain. In frequency domain, you need 240 subcarriers. 240 subcarriers means 240 by 12. That means 20 resource block. Now this 20 resource block and 4 symbols will carry the entire SS block. If you look at primary synchronization signal, this one, PSS, it requires 127 subcarriers. And that will be, if you start from say 0, of course, RB number will be different, 0 to 240. If you look at from 56 to 182, subcarrier number 56 to 182 is your PSS at symbol 0, and this is at symbol 2. Secondary synchronization signal at symbol 2, 127 subcarrier, and physical broadcast channel will occupy the entire 240 subcarriers, and then you have PVCH at symbol 1. The entire 240 subcarrier is for PVCH, and some more in symbol 2, this particular size from subcarrier 0 to 47, and from 192 to 239. You have 4 RB here, 4 RB here for physical broadcast channel. So this is the structure of SS block. Any question here? So please go through it. That
no, sir.
PSS will require how many RB? SSS will require how many RB? This type of question will have in quizzes. And this is the region I can have only a minimum channel bandwidth of 5 megahertz. This is the region because I require 240 subcarriers for SS block. That means 20 RB. And you recall, if I have 5 megahertz, I'm able to have about 24 RB or 25 RB. If you have less than that, it will be less than 20 RB. And since synchronization signal cannot be sent, so communication will not be possible. That's why minimum channel bandwidth requirement is of 5 megahertz. Is this clear?
Yes, sir.
Yes, sir.
Okay. So can we calculate bandwidth of SS block? So 240 subcarrier, and if I use 15 kilohertz subcarriers, how much bandwidth it will come? 240 into 15 kilohertz. How much channel bandwidth? I need your help. Any of you, please?
3600.
Okay, 3.6 megahertz is required for SS block itself. If I use 30 kilohertz, it will double to 7.2. If I use 60 kilohertz subcarrier spacing, then bandwidth is 14.4. Then 28.8 megahertz and then 57.6 megahertz. And now you recall that in every subcarrier spacing, the minimum supported channel bandwidth, right, is given. That all because of support of, suppose I have 30 kilohertz. So bandwidth of SSB itself is 7.2 megahertz. That's why, if you recall, I had a minimum channel bandwidth using 30 kilohertz was 10 megahertz, not 5 megahertz. So if I want to use 30 kilohertz subcarrier spacing, minimum channel bandwidth requirement to support a communication is how much? 10 megahertz. So are
Sir,
you able
if
to
it is a
correlate?
60, for 60, it's around 20.
Yeah. Yes. So that's why there's a minimum requirement of channel bandwidth considering the SS accommodation of SS block. Now, if you read that table along with this, it will make you clear. So I would request you to take a printout or on your screen and compare that. Now, some idea that your primary synchronization signal in a very broad way is used for downlink frame synchronization. UV uses this for synchronization in frequency and time domain in a downlink direction. So what it gives, the way it is decoded, PSS, it gives the radio frame boundary, that is position of first symbol in a radio frame. With PSS, my device will be able to identify the first symbol in a radio frame. And then we know that 127 and all. It also gives a value called N2. It also gives a value called N2, which is utilized to calculate primary cell ID. PCI you might have heard. So N2 value is coming from PSS. If you look at SSS, this gives the boundary of a subframe. This gives boundary of a subframe. So now we know the boundary of a frame, you know the boundary of a subframe. So you are able to synchronize in some sort of time domain, right? And this also gives you N1 value. We call it N1. So this is also used to calculate PCI, primary cell ID. Okay. So how do you calculate primary cell ID? So now you know PSS gives N2 and SSS gives N1. Using the N1 and N2 value, I can calculate physical cell ID or PCI. How to calculate? So basically, suppose SSS value is 303. This is N1 is 303 example, and N2 is say 1. N2 is say 1. PSS is 1. So how to calculate? Multiply this by 3. So it's coming 909, and you add this in this 1. So it will come 910. So my PCI is 910. Okay, this is how system calculates, your UV calculates the physical cell ID on which it will be latching. Okay. So there is some noise coming. Can somebody mute?
अच्छा, बेसिक साइंस का भी बंद है क्यों?
Thank you.
बस तुमको जब पूछूंगा तो बेसिक साइंस कब चल गया था ना, आज भी बेसिक साइंस में कुछ काम हो रहा है.
Madhukar, can you mute him getting a noise?
Yes, sir. Muted. Muted.
Thank you. Now, another concept that how to, now time domain we are able to synchronize in terms of frame and subframe. And you know, in time domain system has synchronized, but in frequency domain, how to synchronize. So in frequency domain, so what happens is like there is a concept of synchronization raster. There is a concept of synchronization raster. That means when you switch on your mobile, there are certain fixed frequency point on which this SS blocks are available. There are certain fixed, and those are called synchronization raster. These are numbers, right? So on that, your UV tries to see on those frequencies availability of a SS block. So it is used for system acquisition. So for all frequency, the global synchronization raster is defined by 3GPP, and you can calculate absolute frequency if you know the GSCN. So your device will have an idea to calculate SS ref, that is absolute frequency of SS block, using the global synchronization channel raster or channel number GSCN. Okay. Okay, so just look at I talked about global synchronization channel number. Against every number, there is a specific frequency point, and on these points, my device looks at for finding the SS block. But question is that what is the numerology used when I am able to synchronize? Since I am switching on for the first time, my mobile is trying to latch for the first time, on which numerology I should decode. So those are predefined. For example, if I use numerology 0, then I'll be so in FR1. So FR1 frequency less than 3 gigahertz, I'll be using 15 kilohertz subcarrier spacing for GSCN, right, or SSB. For then if I have a 30 kilohertz in FR1, I can use more than this is less than 3 gigahertz, more than 3 gigahertz. Then I can use 120 kilohertz for FR2 and 240 kilohertz for FR2. These are different numerology defined. Okay. So how to see the synchronization raster, global synchronization channel number. So these are defined in the standard. So if you look at this, that frequencies up to 3 gigahertz, this one, the GSCN number starts from 2 and ends up to 7498. Frequencies from 3 gigahertz to 24.25 gigahertz, the channel number, the GSCN is starting from 7499, goes up to 22255. And beyond this, it starts from here and goes up to here. So if you know the GSCN, you can calculate the SRF, the absolute frequency, using this formula, right? So what I want to tell you that here the step size is 1200 kilohertz. The synchronization signal will not be at any point. It will be like if one synchronization signal point is this, the next will be after 1200 kilohertz. In case of this frequency, in case of this frequency, this is 1.44 megahertz from 1.44 megahertz. So step size of searching for SS block is 1.44 megahertz. And then step size in millimeter wave is 17.25 megahertz. 17.25 megahertz. Now I'll ask you a question whether you have understood or you want me to explain it further. Shall I proceed?
In previous
Yes, sir.
slide,
Yes, sir. Yes, sir.
we completed with
Okay.
N1 into 3 you made, no, sir, in the previous slide, N1 into 3 plus 1.
Can you ask this question?
Sir, am I audible, sir? Am I audible, sir?
A little bit. Just ask your question.
Sir, in the previous slide, N1 into 3 you made now, sir. How it is? 3.
Okay, you are talking about this one?
Yes, sir.
So here, example I gave, N1 can be from 0 to 355. Example I gave, suppose N1 is 303.
Okay, sir.
So you multiply this by 3 and add the N2 value, which I said, okay, let's assume 1. It can be 0, 1, 2. So if you add.
Multiplied by 3, sir?
Pardon?
Why you multiplied by 3?
So this is the way we calculate PCI. So how many PCI would be possible from 0 to 108, the physical cell ID range. So I have to convey the physical cell ID of the cell to the user equipment. And the way I tell is that like I transmit primary synchronization signal and secondary synchronization signal. In primary synchronization signal, I am sending 3 types of pseudo random sequence, and based on pseudo random sequence, the UE is able to guess whether it is 0 or 1 or 2. In case of a secondary synchronization signal, I send many type of pseudo random sequences, and based on that sequence, UE is able to detect whether it is 0, 1, 2, 3, 4 or 3, 3, 5. And once it knows N1 and N2 value, it can calculate physical cell ID. That's the idea followed.
Okay, sir. Thank you, sir.
Because initially, no, I cannot tell in a simple way that PCI is so and so, because your UV and the network is not synchronized. They are not able to communicate to each other as of now because they are not synchronized in time and frequency domain. And they require to know the PCI to further proceed. So this is the way PCI is transmitted.
Okay, sir. Thank you, sir.
Okay. Okay, so this is some calculation I have done for different band, how you can calculate frequency from the GSCN. You can try yourself. I'm skipping because of the time. The one difference between 4G and 5G is in respect of the SS block, that in case of a 4G, SS block is always at center of the frequency. So it was easy for UE to identify that where the SS block is in the frequency domain. In 5G, it can be at any point because of the BWP concept. So SSB can be anywhere, not necessarily at the center. And that's why standard has given that how to locate. Okay, so location of SSB in time frequency domain, we have seen how it time domain we can locate. So this is taken from the standard that SSB is located at symbol 2. If suppose there are 5 cases, case A, B, C, D. Case A is using 15 kilowatt subcarrier spacing. So my SSB can start from symbol 2 or symbol 8, or maybe it can start from just add 14. So symbol 16 and then add 8. Okay, so that way my SSB can start, right? If my frequency used is less than 3 gigahertz. If my frequency used is more than 3 gigahertz, then I can have 8 number of SSB block, right? So here I'm having 4, here I'm having 8. If I use 30 kilohertz, so again I have some number of. So if you see the below chart, less than 3 gigahertz, I can have up to 4 SSB. 3 to 6, I can have 8. Millimeter wave, I can have 64. These SSBs are how it is utilized. Just see this example. I have broken that table into smaller part. Suppose this is the time grid and I have taken 1 millisecond and 1 RB only. 1 RB only, whereas it will be 240 or 20 RB for SSB. So where it is starting from symbol 2, and I'll have 4 symbols for SSB. So 2, 3, 4, 5 number of symbol for SSB. The next would be starting at 8. So 8, 9, 10, 11. 8, 9, 10, 11. So if my frequency is less than 3 gigahertz, right, then if I'm having only 2 SSB. So it will look like this, where these SSBs are placed in a one subframe. Suppose I have 8 SSB synchronization signal block. So one will start from 2, other is 8. The next will be if I put the value 1, this one. So then I'll start from 16 and then I'll start from 22. So these are SSBs in case I'm using 15 kilohertz and using this frequency band. So I'm having more number of 4 number of SS burst in this case. If you plot this, you'll get 8 number of SSB. So 4 number here, 8 number here. Frequency less than 3 gigahertz, I can have up to 4 SS burst. So how this SS burst are used? Just so again calculation. So in case I use 15 kilohertz, n is equal to 3. So I can have 8 number of SS burst. In yellow color, you can see I have plotted various subframe, 1 millisecond, 1 millisecond, 1 millisecond. These all are I have done in Excel to explain you. So what is then SS burst? Just see this picture. Now we know the SSB. So within 5 millisecond, I can transmit multiple SS burst. As we can see that symbol 2 starting, symbol 8 starting. So within 5 millisecond, that means within 5 subframes, right? Within 5 subframes, I can either do 4 SS burst, or I can do 8 SS burst, or I can do 16 SS burst, depending upon what numerology I'm using. Okay. So this is called SS burst. Whatever number of SSBs are transmitted in 5 millisecond is called SS burst. And then starting from here, only after 20 millisecond, another cycle of SS burst can start. SS burst set can start. Every SB which you see will be transmitted in a different beam. You must be knowing about beam forming concept. Every beam will have different SB. So for example, if the user is here and it is receiving a signal from this beam, so it will not select. If the user is here and then beam is straight away coming, so it will select. Similarly in the uplink direction. So which beam? So UV, if UV is here, so this will select SSB3 would be useful to synchronize. If UV is here, SSB2 will be for him to utilize, and so on. Is this clear? Is this concept clear to all of you? Please say yes or no.
Yes.
Yes.
Okay, this is my last slide. That what is the overall synchronization procedure? So first of all, your UV is trying to receive this SS burst, right? So trying to receive SS burst, and then it will decode those PSS and SSS, and it will know N1 and N2 value. So it is able to calculate the cell ID, this process. Okay. And then it is also able to decode the PBCH, DMRS and MIB from PBCH, and it knows multiple information here, like subframe number, RSRP, SSB index, many information it will know that. Then what will happen is the RAS resources will be random access resources will be allocated to the UV, and then it will do we call it message 1, message 2, message 3. You may be knowing RAS procedure is like that. So that way up to here we are able to synchronize in downlink direction, and here we are trying to synchronize in uplink direction with RAS procedure. And once that is done, we will have a connection established, and from here I can transmit the data, right? So this is how, in a very, very small way, NR synchronization procedure looks like. Now I'll tell you about tomorrow's session. So tomorrow session will be by Avesa IT Roorkee, wherein he will talk about different channels, and also he'll talk about especially PDSCH. PDSCH is shared channel where user data is transmitted. If you look at the grid, the first 3 symbols are for control channel, and then we have a DMRS, demodulation reference signal. All these blue are PDSCH, where data is transmitted or uploaded, DMRS again and again we have a data. So this is the overall the grid structure in a very short way. So tomorrow he'll talk about different NR channels. So you have physical channels, you have transmode channels, you have logical channels. His focus will be on PDSCH, whether data get transmitted, and he will briefly cover all these aspects. I think now you'll be able to understand with the knowledge of all those aspects which I explained. So with this, I should say thank you so much to all of you. In case you have any question. Maybe we can open. Namaskar, Mathur Saab, in case you are able to speak now.
आवाज आ रही है अब?
अभी clear है sir, पूरा clear है.
It's the clear, sir.
It is wonderful listening to you, Ashok ji. मतलब अभी बीच में थोड़ा सा 2 मिनट आपने अपने लोकल फ्रेंड्स जो हमारे हैं इसमें उनके साथ में बात करी 2 मिनट, तो they were all surprised कि being in a government setup and having a prime responsibility of managing field, I mean field duties, you are able to take such a heavy lecture and that too for 4 continuous hours. I mean, hats off to you as far as your teaching capabilities are concerned, and it's wonderful. बाकी देखिए आप लोग चुपचाप बैठे हैं तो इसका मतलब ये है कि सारी चीजें समझ में आ रही है.
Anyway, so sir, recording will be available many a times, so you may not focus, so one can go through recording. It's always available. We'll make this available, sir, to everyone.
It has become a very convenient way of learning, जिसमें those who can manage, I mean, of course, हम तो चाहेंगे कि maximum time हम आपके साथ continuous direct interaction के साथ में सीखें, लेकिन बावजूद उसके आपने you are making everything available as recording and as your other resource material over YouTube. So it's a wonderful opportunity to know more and more. And rather, you can say, for the first time, we are learning so many things.
Thank you, sir. Thank you. Any more comment from anyone before we close?
Sir, really your today's lecture was so good that we feel we have to write this time the paper or research paper definitely in the 5G, 6G technology. And last session, and we could able to correlate because last time you told that autonomous vehicle, and really it's useful for the universities or some closed nowadays all the communities are closed communities, and we are not finding the drivers and other thing. For children and elderly people, we can able to monitor if really we can think in a different, we all from the all over India we are participating. We can look into the different cities and how it is the need of this technology. And your insights, the way you explained, we able to recollect that during our engineering time, the communication subject, we can able to recollect easily with your this thing. Really, it was a wonderful, sir. The way, the pace you covered the syllabus and all those things. It's a lot to learn, but you explained in very 4 hours convenient time. You explained nicely, sir. Thank you very much for.
Thank you. Thank you.
Fortunate to join in this course, sir.
Great. So any more comment or shall we close? It's already very late.
Sir, today we will close, sir. We'll go through one more time. If you have any doubts, in the next session we will ask doubts if there are any.
Please.
After going through one more time.
Yeah. So maybe my next session would be on 5G core radio. From my side, I have done with, and tomorrow on the radio part, more in-depth thing will come from Professor Shah, and some of you have also like volunteered. So those specialized session will be there. From my side, radio I tried to complete today. Next time I'll be having 5G core. Thank you.
Thank you. Thank you so much.
Thank you, everyone.